Get kind of going. And hi, everybody. We're really excited to be here today and introduce to you kind of methodologies and best practices for thinking about data, working with data, and using data to make decisions. We are using a couple sample data sets that might seem like they're very specific in case, but in reality, we really want you to be walking away with you can use these things, these techniques, these practices that we're going to be talking about today for any kind of data set that you have. So we're going to talk about some best practices for when to use spreadsheets, when not to use spreadsheets, how to use more kind of data science centric programs like RStudio, and how to do different kinds of analysis, clean your data, and produce visualizations of your data within R. And then we'll kind of see how that all is working for everybody. We hope to have a dynamic session. How this is going to work is Dan is going to be leading you all through most of the presentation. I'm going to be in the chat to help anybody out along the way. You're more than welcome to message me directly or to message the entire group, whatever you feel the most comfortable with. I am going to go ahead and start recording with everything. To this computer. And get us moving with our workshop today. So that's kind of the gist of everything of where we're going. And so I'm Dr. Ann Brown. I am an assistant professor here at Virginia Tech, and I am a molecular modeler by training, but I work a lot with data science in a variety of capacities. I'm also a big proponent for open science and data reproducibility, and highly encourage you all to think about that as you work with data in the world of healthcare, because it's becoming so important about the kinds of data we have and what we're collecting. One thing I do want to mention is that we're both recording this information. I'm going to have some links in the chat as well, where we have the written versions of this material for you to follow along, and that's going to be continually open and accessible for everybody. We have the slide decks that we have that we're going to share with everybody. And then I have a couple other links as well that I'll make sure we all have. But if Dan, if you'll go one slide forward real fast. All of this will be here. We also, if anyone is interested in working with a research study that we're doing on how we actually train and think about training individuals in the healthcare fields in data, we have some links for that as well. We would highly appreciate any addition to that, and I'll put those links in the chat as well if you're interested in participating in our research study. With that being said, we welcome you all to learn about data science in this capacity and how it relates to healthcare. And I will turn everything over to Daniel Chen, who is going to be leading us through this and is really focusing a lot of his dissertation on how to train individuals in the biomedical health sphere in data science techniques.
Hello. So my name is Daniel Chen. I am a data science educator. I'm also a PhD student at Virginia Tech, and a lot of the work from today's workshop is related to my dissertation in terms of the education and pedagogy aspect of teaching people who work in the biomedical sciences. Some additional background, I interned for RStudio last year in 2019 and worked on their education team. Part of the Carpentries, which is a volunteer organization that tries to teach people the programming and research aspect of doing research when that's not your actual background. So a lot of the materials that we're working with today stem from the Carpentries or are inspired by them. And so that's another resource for everyone as well. And there's going to be a slide deck at the end with a whole bunch of other links for additional things. So just to reiterate, that third link doesn't exist. But you can find all of the lesson materials. It's actually pinned on my video on the bottom. That's just like as the blank text if you forget. The slides that you see and the papers that I reference are also in a Google Drive that you can have access to. And just in general, if you have a technical word that you don't know, you can either ask today, or there's also a glossary that's been started up and maintained by the Carpentries. So if you need to look up like a really specific piece of jargon, there's a glossary site for that as well. So for today, this is sort of a hands-on workshop. And the tricky thing is, if you only have one screen, how do you manage like the screen that you're looking at from me, and also like how do you manage the rest of your screen to follow along? This is one example of how you can set up your screen. I think this is if your screen is on a like the resolution is like 1080, where you would have the like my current Zoom screen on the top right corner. We will eventually be working with RStudio, so you'll have your RStudio as big as possible on the bottom left, and then you can have the Zoom chat on the top left, and then you have a space on the bottom right for your own notes or something to follow along. This way you can have access to everything all in one screen, and it should be big enough for you to follow along. If you end up going to the website in the future and you end up seeing this page not found, like if it works right now, but then immediately after you see this error message, it's because I am doing an update to the website, and the website usually goes down when there's a website update because it has to rebuild everything. So if you see this page not found error, that's probably because I'm working. So a lot of this work comes from a research study that started in the summer of 2019, where we asked people around campus who work in biomedical sciences what are their attitudes towards how do they think about data, how do they think about having raw access to data, and where does programming fit into all of this. And so it's really trying to bridge the gap of, yes, people work with data because they need to answer some kind of question for business or for some research project. And they need to be able to reproduce or update like their findings without going through a lot of manual tedious work. So one of the goals for today is how do we slowly start to automate that process, and how do we think about data in such a way where if we do work with an analyst, sort of make everyone's lives easier because of the way the data is structured. So one of the things that came out of this research study was also a set of personas that essentially try to personify like the type of people that would attend this workshop. And do this now, but yes, it is sort of worth like going through the personas and then trying to see which one of the four that you identify with. It might not be perfect because the study sample is mainly from the academic side, and everyone here is a working professional in like a clinic. So there might be some differences in terms of the exact wording of things, but that's sort of where this research study came from. So we are going to slowly dive into R as a programming language. And so just so you know, yes, it's learning how to do data analytics and thinking about your data in that way is difficult. There's a very steep initial learning curve, and then you slowly realize that if you keep going at it, it will be a little bit easier until you realize there's a lot more stuff to learn. But there's actually a very large and helpful community behind all of this, where if you have a problem, usually someone on the internet will be. So one of the things when you're learning something like this, that there are phases into dealing with your problem. For example, this morning we had an issue just installing things, which is actually one of the larger hurdles, because if you can't get anything installed, then you can't actually like do anything else. And so just know that yes, it can get frustrating. There's people that are available to help you, and this all happens to me as well, where there are times where things just get frustrating. But just keep at it, and eventually, hopefully, the automation process will pay off. So, like I said, there is a very large community. All of these illustrations were actually drawn by another professor in the community, and so there is a lot of ways for people to help you learn all of this stuff. And so for today, there's a lot to cover, but the main goal is not really to have you redo every single thing when you're thinking about your data sets for your question of interest, but the main goal is when you are sort of curating your own data sets um, for your business purpose, that you're curating them in such a way that is useful for analysis and to help you answer the question that you're interested in. So with that, uh, the first step or the first chapter for today is really just learning about spreadsheets. So the first exercise, you don't actually have to do this, but we'll take a minute. And let's say you are working with a few patients and you're asked to keep track of their base vital signs. You can imagine this is for like a pharmacokinetic study for a drug. And so you're just trying to monitor if this drug is safe for the patient by looking at their vital signs. And so we have 3 patients at 3 different times and different readings for heart rate, respiratory rate, blood pressure, pulse ox, and temperature. So you can do this in an actual spreadsheet, but just imagine how you would actually go about inputting this data into. So one solution, one solution that you can do is you input all of the values with the title without any units. And so this is one way you can do this, but there are certain things to think about when you're inputting data this way. Maybe everything that we're working with is completely specific to your clinic and you don't have to worry about temperature. But the second you think about collaborating with other people, depending on that, temperature might also be written down in Celsius instead of Fahrenheit. Things like heart rate, respiratory rate, those are probably the unit is known as like some kind of rate. So like counts per minute. Pulse ox is usually almost always a percentage. So certain things you can assume, and certain things are not always going to be as clear depending on who you're working with, right? So one way you can fix that is maybe you directly input the unit information straight into the number. So, the percentages are actual percentages, the numbers, the temperatures actually have a unit with them. But now, if you do this, one of the problems you end up with is when you try to do the analysis, this happens even in Excel. Let's say I want to go and like take the average temperature reading. The fact that I put the letter F in there, Excel won't be able to do a mathematical calculation because that F turns that number into not a number, right? So that's one problem. But the good thing is, at least we're really explicit with like the unit, so no one can actually mess that up. Percentages, Excel can kind of understand that as well. But if you think about it from more like how can I set up a data set that I can also hand off to someone else to do other types of analysis, that percentage mark also can be a problem the same way that letter F is. In terms of like, oh, it's a number, but there's this other thing, and computers usually try not to guess and you also don't want the computer to guess. So a lot of the frustrations you have with Excel sometimes is because Excel's trying to be super useful when it's like making things worse. Um, and so putting like those bits of information is not really a good idea. The other issue that we have here is if we even look at the temperature number 96.8F, that cell contains two bits of information, right? It contains the measurement, which is 96.8, but it also contains the unit. And so in general, when you're putting together spreadsheets, you want each individual cell to only contain one bit of information, right? So that way you have a lot more flexibility when you're putting together and working with your data down the line if each cell only contains one bit of information. And so that one bit of information also applies to this blood pressure reading, right? Because usually we think of blood pressure like we just read it off as like 128/78, but that is actually diastolic and systolic number at the same time in the same cell, right? So you can't actually go about very easily or right away saying like what is the average diastolic pressure, what is the average systolic blood pressure, right? Because it's containing two bits of information. So one other thing, so when we're thinking about splitting units or splitting things into two separate, or such as it only contains one bit of information, we can do that with name is a pretty common one where we split first name and last name, right? We usually try not to enter data with their whole name in one continuous string object into a cell because we like to be able to sort from first name and last name and stuff like that. So one way you can get around having two bits of information when one of those bits is a unit is you can name your column name such that it actually contains the unit that you're working with. So that way, instead of writing 96.8F, if your column name is temperature in F for Fahrenheit, then anyone looking at this data set will know, okay, these are all Fahrenheit readings. Also, temperature is sort of one of those cases where like if it's in the 30s, it's probably a Celsius reading, and if it's in the 90s or 100s, it's probably in Fahrenheit. So you can sort of like if someone were to input the wrong unit, you'll be okay. But not all units are that like discernible when you metric to imperial. And so one solution that you can have is splitting out the name, splitting out the blood pressure, such that you have a column that's diastolic and systolic. You have a column that's like temperature, the unit itself, and then sometimes you might just have a column that is just the column of what unit it is. So this is one example of how you might have set up your data. Chances are, like even when I was going through this isn't usually the data format that I come up with right away, but it becomes really helpful down the line because now every single cell only contains one bit of information. And if it's a number, I can now start doing these quick calculations of like what is the average, or like if I take multiple readings from the same person, I can see averages by person, right? So the main takeaway is really only put one thing in each column, right? And that includes like colors. Like, yes, you can use colors to help you visualize your data, but a color should not be the thing that is part of that cell when you're thinking about it from like a data perspective, because a color also adds another bit of information to a cell. So we'll take another minute. So let's say you have two more readings for those three people. Right. So think about if this was a actual PK study and you took the first reading and now you get another set of readings as they're coming in. How would you change like the spreadsheet that you have in your head right now? How would you enter the new patient information? Take about a minute to sort of think that through. So one solution you might have, um, and each of these solutions, none of them is more or less valid than the other. They all have their different use cases. But one way you can have is, okay, I know I'm going to be working with a bunch of patients. Let me create either a separate sheet or a separate Excel file for each patient, right? So you might end up in a situation where you have three separate tables for each of your three patients. And this could be good. This is useful in the sense that you're trying to visually check your work. You're missing an Excel sheet, you probably are missing that patient's information. So it's easier to find like missing patients that way. Once you open the sheet, you can very quickly know that like this is all pertaining to one person. And so you can create these one person level statistics pretty easy. Just know that down the line, if everything is separated and you need to answer the question of like, what is the average heart rate across all of my patients, you need to do some other step to combine all of your data together, right? So each data format does have a use case, and as long as you know what the steps are in the future, have some plan to work with it that way, then this data set works for your use case, right? So when I was an analyst doing clinical trials, I believe all of my data sets were individual patient based because it was way easier to figure out what's missing. And like, this is the patient that I'm working with, and this is only the information I need to be looking at right now, right? Another solution to this would be everyone's on the same sheet, but you have some kind of marker to like split up patients, right? So this is pretty common in the sense that like, oh, I have multiple people. I'm going to enter them all in the same sheet, but I need them visually split so I can actually do that visual checking right away, right? So this works in that later on, you don't have to join it all together into one table. It's all right there. But the issue then becomes when you start passing off this data set to other people, or depending on what, I don't think this applies to Excel. It does apply to Excel. So when you start calculating statistics, for example, like I want to convert Fahrenheit to Celsius because the clinical trials people all work in, the drug companies all work in Celsius. If you do that formula conversion in Excel, like all of those blank rows, you'll get that like pound, 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 like ref question mark problem. And that makes sense in our case because there's literally a blank line and it can't do that calculation. But that slowly becomes problematic when you need to work with your data set, like, and doing the analysis part. Right now, it's perfectly fine if it helps you input data correctly, right? So there's like really two steps in the data process. Like, use the data format that like makes it so like if you're manually having to enter data or curate your own data set, that like that part is accurate. Like, that's actually really important. So whatever system makes that part easier for you, go with it. Just know that like later on there's going to be steps that you need to do to like process or clean up that data. So another thing that you can have is, instead of stacking your patients vertically, you stack your patients horizontally. So like maybe cells A to M is like patient number one, and then N to Z is like patient number two, and then AA to A like patient number three, et cetera, et cetera. That way, they're all in, there's no blank lines anywhere. So that's a good thing. Everyone's in the same sheet. But then your problem is you wouldn't really be able to ask the question of like, what is the average heart rate across all my patients, because you can't actually select a single column. Stuff like Excel, Excel has a maximum number of columns that it can actually hold, and this was an issue very recently. Britain, where their COVID information was all stored day by day, where each day was a separate column, and they literally just ran out of columns. And And so when you're thinking about your data set, it's much better to work long-wise than appending columns, like making new things of new columns. Um, in some sense, uh, if your thought process is mainly like I'm just gonna add a new column to the end, maybe it's better to like create just like another data set for that new day, right? So another example that's not medically related is like stock data. Um, Usually you can get stock data by the day if you're looking historically, and so each day would be its own separate spreadsheet, right? And then you combine them lengthwise as you need, but you're not tacking them on to the side. And that's mainly because um, spreadsheet systems like Excel will literally run out of columns. um, Sometimes databases actually don't like it when you do that. So a lot of systems don't like it when you append data column wise, but you can just keep appending things row wise. And also, technically, Excel has a maximum number of rows it can store, but that's usually in the order of millions. But the column limitation is like in the order of thousands. So you can hit that column limitation pretty soon. So one of the actual solutions is you just dump all of your patients as in the order that they were coming in. Um, and in Excel, you have the option to click the little data button and you can sort things. So you do have the option of like still finding out like if patients are missing data, um, or better yet, or the nicer thing now is because each column is its own separate variable and each cell really only contains one bit of information, you can then start asking those questions of like, what is the average heart rate? Or Excel has like that built-in grouping function where you can say like, I want to group by like last name and first name, and then calculate the average heart rate. So then you can start asking the question of like, what is the average heart rate for each of my patients over time? Also ask the question of like, what is the average heart rate for everyone at one time? So the other main takeaway is you can set up your data as you're curating your own data set. Um, just know that any decision that you're making when you're curating data, there's always going to be some process with it later on. But as long as you know about what you can do or plan ahead, then it's not really messy in a sense of like, I can't deal with this thing, it's a wreck, right? So, and hopefully today they're in the third hour, we'll show you all of the techniques that you can actually use to like clean up your data set. Um, so as long as you have a plan for how things are set up and convert a messy your data input into something that's a little bit more suitable for like a computer to understand, then it's not as bad to deal with than like I have this thing and I can't deal with it because it's such a mess. Right? So having a plan is one of the things that we're hoping to show you today. So the last thing to think about is, let's say we have that data set, and according to the clinical trials guidelines, there are adverse event things that you need to report. And so like there can be a bunch of criteria that's for an adverse event. How would you go about flagging those people um, that they have an adverse event? Right? So you have this imaginary data set, have like a data dictionary of like, if any of these things is true, then you need to like report that to the pharmaceutical company running the trial. But also like before you go reporting, you need to identify those people first. And so how would you go about identifying those people? So one thing that we can do, and it's sort of very common, is you literally find those values that are problematic and you highlight them, and then you click like the little paint bucket button in Excel and you flag the cell some color, right? And so this is really good in the sense that like you as the person trying to figure out who or what value is bad very quickly, because there's now a visual cue to say like, hey, this is a bad value, right? The problem is if this was a million rows long, that becomes a very tedious and manual process. And depending on how the data is sorted, like if it's by patient or by time, you might not very quickly be able to see all of these bad values. Other problem is if we look at like one of these cells, for example, Anya's diastolic value of 142, that cell contains 2 bits of information. It contains the actual diastolic value, but then it also contains whether or not that value was good or bad. And so it is a cell that now contains 2 bits of information, which if you were to give this Excel sheet to an analyst that doesn't use Excel for their work, that color doesn't show up on their end, right? So like if you were to give me an Excel sheet and I were to do my entire analysis through them, I would not see the 142 as being red. A lot of programming languages do not, they just take the value and they throw out all of the other things that's not a value. And so color becomes one of those things where like it's great when you're inputting data and if you don't have that much data to work with, then it's okay. But then it very quickly becomes very problematic because now you're relying on visual cues to tell you like who to look for. And this can be done in Excel with like an if statement or a conditional statement with a color. But then you're now looking for color and not an actual value, which becomes a problem if you want to do. And so one thing you can do is you create a separate column, and that column is simply a yes or no column of saying like, hey, I need to report this case, right? So you can use this in conjunction with a color if that helps. But this way, when you give your data set to someone else, they can essentially say like, hey, you can essentially tell them like, hey, I know I used colors, but I also gave you this column that says like, hey, these are the columns that you can look for just to filter values out, right? And then so me as the analyst or someone else, they can say like, oh, I need to find all of the cases that are problematic. I can filter on a value of yes or no from a report column. I don't need to filter on a color of a cell. And then this way, you can very quickly go down and like start seeing like, okay, which of these did I miss? Like maybe you're only flagging the yeses, and so you want to be able to filter on the cells that you left blank and to double check that you're flagging the right ones. Or you can write like a conditional statement in Excel that says like, if diastolic, or like if a column A is like greater than 140, like input YES, right? So you can do all of those things in Excel, and then now you have a very nice way to nice column that you can use as a filtering column. And filtering by column is much more convenient and reliable than filtering on a color. So the main takeaway here is when you are curating your data, it's fine when you're inputting data to make your life easier, but because you're looking at an Excel sheet, it's very, like I fall into this trap as well. It's very tempting to treat the Excel sheet itself as a data visualization and not actually a data set that you can work with. Right. So even when I'm curating data sets, sometimes I'm like, oh, I'm typing all this stuff in. I just need colors just to tell me I'm doing things correctly. That's fine. Just know that that is not part of the data set that you're going to hand off to someone else. And so, the last exercise is really just, what if the person's heart rate was elevated because, they ended up doing like yoga in the middle of a PK study, and that's why everything's awry. Yes, always leave yourself some kind of column just to like take notes for. Um, because we're using programming languages like R that can handle this stuff. I like to just have all my notes in my data set itself, so I don't so everything travels together. There are things like SPSS and SAS. They typically don't like full blown sentences like in their cell in the data set that you're giving them, and that's why a lot of times when you're working with health data, that's not something that you put together. There's like the data set that's nothing but numbers, and then like this 500-page PDF that just corresponds like, oh, one is like what this means, and two is what that means. Um, in some sense, that's nicer on the analyst in the sense that everything's a number. So if I want to do statistics, everything's already a number. I don't have to convert it. The bad thing is when you're trying to just explore your data set, you're constantly jumping back and forth the code book, and it would just be way easier if this thing just told me like this person's like did they take placebo or treatment instead of looking at 0 and 1, right? Because then you can very easily flip those two in your head without referring to the code book. um, so just leave yourself some room just to type everything in. um, Languages like R are nice because it can handle like free form text without having to transform everything. So the main summary for our spreadsheet chapter, before we start working with this from the programming level wise, is spreadsheets are really good when you're trying to manually input data, but try not to treat them as a visualization. So it is a graphical user interface to your data set. Like you can see it, and what you see is exactly what you get, which is really good. Um, the main problem is when you start to do other things. Example, if you want to fit a statistical model to figure out like what next month's projections might be, those things become a little bit more difficult uh, when you're in a spreadsheet program. And so but they do have a very legitimate place when you're trying to manually curate data, or if you just need to figure out like what is going on. Like when you double click a file, it opens up a thing so you can visually check it. So it is useful in the process. Just know that there are limitations to what they can do. Hopefully by the end of today, going through this process, we can up on like hurdles that you might have with Excel and sort of start building like a data pipeline where if you have a data set, you can do your own small calculation and then still have your original data set that you can give other people, or you can have a data set, do one of the transformations that I'm going to show you, and then now anytime you update your original data set, you can run your program to do that calculation and you have something that back in Excel that you can work with much easier. So the next part is going to be on data. We'll go through a little bit of this before we take our first break. So what we're going to do is, how do we take one of those Excel sheets that we have loaded in Excel, and how do we bring that into our computer? System, the programming language that we'll be working with is R, and the system within R is, if you've never used R before, there is a sort of a sub system called Tidyverse, and that's the one that we are going to cover. There are many other ways you can use R to manipulate data, but this is the word you Google if you end up having questions about the stuff I'm showing you today. So the first thing that we need to know about when we are trying to load a data set is we need to know how to find the data set to load. If you've ever worked with a programming language before, sometimes, especially if you work with other people, loading in the data set is like probably the first thing that you're changing as you're like, oh, like here's the work I did, like running on your computer. This is probably the bit that you're changing because someone else's computer is not exactly set up as your computer. And this all has to do with file paths, right? So like, if I have a file on my desktop, if you're on a Windows computer, that file on your desktop is actually in a file that's the whole entire like location in your like C drive is going to be like C drive in the users folder, in the folder that's your like user, and then from there it's the folder called desktop, and then that's where your files are, right? If you're on a Mac, it's going to be in a folder called slash, which represents like the beginning of your computer, and then it's your username, desktop, and then the folder that you're. Uh, and so we're going to have this entire setup on our computer. But before we do that, take a break. And what I want people to do go to this webpage here. You should end up on a page like this, and there is a button called code, and I want everyone to download this zip file and put that, like extract the file on your desktop, right? So I'm going to click download zip. I'm going to save this file. I'm going to dump it on my desktop. On my desktop, I can zip it onto my desktop. I should have a folder like this on my desktop. So that's what we want to do for now. For those of you who uh, have RStudio set up with all of its libraries, etc., on the main website, which you can find like bottom of the screen, there's a section called setup on the left hand side and a section called binder. And if you click this first link, give it about like 30 seconds, it will open up RStudio with the data files all set up for you. The main problem is this doesn't persist. So like after today, all of the things that you would have typed will not be there anymore, which I can show you at the very end on how you can save this. But so that's one of the downsides, is none of this persists. But it does set it up so you can at least follow along on your computer. So we will come back at 10 o'clock, assuming everyone's on the East Coast. And hopefully by 10 o'clock, you have this zip file on your desktop, or you got this binder link, which I will paste in.
Thanks, Dan.
All right. We'll come back at 10, everybody. Thank you for everything. If you have additional questions, please feel free to shoot myself or Dan a message in the chat, or unmute and ask, and we'll keep moving from there and work with RStudio in just a few minutes.
Thank you. Thank you, Dan, and appreciate it.
All right, everybody, we are back at the 10 o'clock hour and jumping into getting started and loading data into our studio. I want to highly encourage you guys, as well as we're getting going with this. If you have questions about your own data that you have or you might be working with, please do feel free to unmute or put something in the chat that I can integrate into our session because we do want this to be as useful to you as possible. So we've got a small group, and I think we can make sure we answer any and all your questions you might have at these points in time. So don't hesitate on that front, and we'll get Dan going on how to load data into R. Does everyone have either their binder link up or RStudio and the data downloaded on your computer? Get a thumbs up for that real quick. All right, awesome, awesome, awesome. Thank you. All right, Dan, here we go.
Okay. So if you open up RStudio, might have a panel that looks something like this. When you first open up RStudio, either on your desktop or on the web interface, there are three main panels that first show up. The bottom right panel, by default, will show the files on your computer. So if you're using the binder link, this is the files on that computer somewhere on the internet, not the files on your local computer. Binder link does have the data sets loaded and everything should be set up properly. So you can still follow along. If you're using the RStudio version on your computer, minus the color scheme, the bottom right corner should actually look familiar in the sense that those represent the files on your computer somewhere. The top right portion, there's a few tabs called Environment. That Environment tab, as you start creating and loading up data sets, that panel will start populating with, if you load 5 data sets, you'll have 5 things in the Environment panel. If you start creating variables, for example, like your name, and you start creating those objects to work with, those objects will show up on the top right side. On the left-hand side, this is actually the programming language that R will be using. It will take in commands that you put in, and then it will execute it. So for example, on this left-hand side, if we do something like 3 plus 3 and hit enter, and I need to make this bigger. If we do something like 3 plus 3, it will take that command that you put in and return an output for you. And so we'll be working with this system from here on out. On the top left corner, you should be able to hit something like File, go to New File and New R script. And what this will do is this will open up a 4th panel in your RStudio setup. And here you can now type in like 3 plus 3, but now you have the option to save this file, right? So usually when you're trying to do all of this programming work, typically you don't do work once and then you never do it again, or you have to retype everything. So typically you save all of the commands that you're going to be working with into a file so that when you go home for the evening or for the day, or you go to lunch or your computer restarts, you still have that file to work with. And so the top left panel will open up the ability for you to save the stuff that we're working with. A few settings, if we can go to Tools on the top, and then we can go to Global Options, there is a few settings that you want to make sure are set up whenever you, like one of those first-time setups. There is a section here called Workplace that says restore.r data to workplace at startup. Make sure that's unchecked, and then make sure that the save workplace to R data on exit is set to never. And what this setting does is, by default, when you open up R or RStudio, it's going to take the last thing that you worked on and automatically load it up, which is great if you only ever work on one project at a time. It is not so great when you have data sets from like more than one project. So let's say you're working on a clinical trial plus also trying to figure out like the finances for that clinical trial, and they're two totally separate projects. What it will do is it'll load up everything. However you closed it, it's going to load all of that up. And it's useful if, that's how you expect things to work. But if you think about, there's two places where that becomes problematic. Let's say you just loaded up like a 1 million row data set and it takes like 3 minutes to load. That means that the next time you open up RStudio, it's gonna just take 3 minutes for you to do anything, because it's going to try to reload all of that stuff back in. And if your job is like to work on a totally unrelated project, you're sort of stuck looking at this thing for 3 minutes. And that also means it's taking up whatever other resources on your computer. So you don't want it to take up resources when you don't want to. Other thing is, when usually the first step when something goes wrong is like the turn it off and turn it back on again. If something were to, like, your code just stops working or whatever, and you want to turn off RStudio, if you don't have those buttons checked, essentially when you turn it off and turn it back on again, it will turn it back on to the same state where things were messed up. And so you don't want that. So this way is a good way to make sure that when you do restart everything, you actually have a proper restart. And this is set up in such a way like you can restart your computer and turn your entire computer off, turn it all back on, and then the fact that you just opened up RStudio, it's gonna try to reload everything back. So you want to make sure those two things are unchecked. There is a section called appearance, and this is where you can kind of like change the color scheme of things. It's sort of nice because it sort of makes this whole setup that you're gonna be looking at more unique to yourself. If you like the little darker-ish theme, I have like the material theme set up, so that's what I'm using. We can leave everything else alone. That's really, this workplace portion is really the only thing that we need to worry. So hopefully we have those files downloaded as a zip file on our computer. If you're using the binder link, you don't need to download it, but the steps from here should also work. On the top right corner, there is a button called Project. And what we want to do is we want to click Open Project. Because the file that we downloaded is already a project that's set up for us. If after the end of this workshop, you want to create your own setup of everything for your own little project to dump your data sets into, you would go to New Project, and you can create a new project from a folder that already exists, or a folder that already exists called existing directory, or new directory where it will create the folder for you. So what we are going to do is, since we already have that project set up for us, I believe. That folder that we downloaded was already set up for us. So we can go to the top right corner. We can click on Open Project. We can use our regular file navigation. Go to our desktop. There should be a folder called ds4biomed-learner. And then from there should be a file called ds4biomed.rproj. We open that. RStudio will do like a small reload. And two things should change on our computer. The first thing that should change is on the top right corner. It should now be the name of the folder that we just loaded, or wherever that file was where we unzipped it. And then on the bottom right hand corner, we should see the contents of that folder, right? So the bottom right should be analogous to the little file explorer or finder window when we're double clicking on files. So hopefully you have two things set up, and just as a small test for everyone to make sure this all works, in the top right corner, we can go to File, New File. We can click on R script, and here we can type, for example, 3 plus 3. And the way we can run this code, like I said before, we can type this code manually on the bottom left-hand corner and say 3 plus 3 and hit enter. If we simply hit enter here, we just get a new line, so that's not very useful. So one way, if you want this 3 plus 3 line to run, if it's a single line, you can make sure that this line, your cursor is on that line, and you can hit Control Enter. I believe that also applies on a Mac. If you're on a Mac, just let me know if that didn't work. What that will do is take that line that the cursor is on, it will essentially copy paste it down here for you and then run it. Another thing you can do is hit Control A or Apple A to select all of the code and hit Control A, and that will run everything that's selected. And if we want to save this file, we can hit Control S or Apple S to save this file. And hopefully it opens up into that folder that we created. And what I want us to do is name this folder 00-rstudio.R. That file name in there. Save. And then on the bottom right hand corner, you should now see that 00-rstudio.R file. So just give I believe there should be a yes. So like in Zoom, there is like the green yes check mark and the red X. So use the green check mark when you have a file saved, you have it opened in the project folder and have RStudio sort of like working. And then give a red X if you need help with something. You can also use the green check mark for like you're ready to move on. Not exactly like everything's working. Still kind of trying to get things set up. If you do have a problem, you can ask it. you're having issues, what problems are you?
My the screen that I had with the binder disappeared. I'm trying to find it now, and I'm still not able to find the files on my desktop. So
If you're using the binder instance, then don't worry about the files on your desktop. It's all contained in the binder instance.
okay.
So if you're in the binder instance, I just pasted the link in the chat again.
Okay.
You
So
should.
can I close the RStudio window that I have open here with all the packages listed?
Yes.
Okay.
If you're using the binder instance, close the one on your computer, because then you're going to be dealing with two things, and that could be confusing.
Oh yeah. Okay.
Yeah.
Let me close. I have so many windows open here. Hold on. Let me close. Do I need this now?
Yeah. So for the binder instance, the steps are going to be the same. On the top right corner, you can click Project, Open Project. Then it should open up in somewhere where you can. I believe it just opens up directly. You should see this ds4biomed R project, and if you hit Open, it should end up in the same situation that I did.
Okay, let me see what you have there. Okay, yes, I'm there.
Yep. And what you should see is like a data folder with data sets in it that we'll work on. And on the top right corner, you should be able to click File, New File, R script. And then you should be able to say something like 1+1. You hit Control Enter. It should execute on the bottom left-hand side. And if you hit Control S to save, it should open up a save window. And the task is to label it like 00 RStudio .r, for example. So that's the file that we create. And so this way, this is like your first piece of R code that you've saved, essentially.
Okay, sorry, go back again. On the right side, do I have to click on data? That's what you said?
You don't have to click on data. It's just the folder with all the data sets. So you should see the data folder.
Okay, and go up to file on the left side.
Yep, new file, and then R script.
Okay.
And that should open up a fourth panel.
And test it to see if it's...
Yep, so you can type. Yep, and you should be able to type anything that you need and hit Control S to save. And then save that file. There's a reason why I said 00 dash, and we'll talk about that in the next, right after this portion.
Do I need to name it something specifically or any file name?
You can, for this exercise, name it 00 RStudio. And then, and I will explain why I'm telling you to name it that way. But in actual practice, you can name this file whatever you makes sense to you.
Okay.
Okay. So now that we have all of those bits working, we can talk about how we can find data on our computer. And so in RStudio, in that bottom right corner, we should be in a folder called ds4biomed-learner. For example, This is an example folder path that you see on the top right side, bottom right side on your computer. And so the folder that we are currently in, and we know that we're in that folder because we opened up that project. So on the top right side, you should be able to, this top right side, whatever, if you hover over it, that location that you see, it's a little bit wonky on the binder section, but you see that it says ds4biomed.rproj. That R project file should also be where we are in the bottom right hand side, right? And so that is the starting point that the computer thinks that we're in. So if we go to our slide deck on showing you where our files are, wherever that our project file is, that is our starting position. So in this example, my working directory or the starting position is going to be on Mac, it would be /users Daniel desktop ds4biomed. That's the starting point. On Windows, it might be C drive users Daniel desktop ds4biomed. In the binder instance, it's going to say ~/ds4biomed. And so now that we know where the starting point is, there's two ways we can reference a data set. One way is through relative path. So knowing that we're starting from this ds4biomed folder, how do we get to the medical data tumor growth file? We can say from here, go to the data folder, and then also go to the medical data tumor growth folder, right? So that's relative to where we are starting. So for R, the way we input that is saying data/medical data tumor growth.csv. There's another way we can specify it, which is essentially specifying the entire full path, right? So a relative path is sort of saying like, how do I get to the Starbucks from my current apartment? Well, it's out the door, make a left, right? The absolute path is, the actual address of Starbucks, like that we type into our GPS system, right? So the absolute path of these files on our computer is from all the way in the beginning. So we can say C drive users, Daniel, desktop, ds4biomed, data, medical tumor growth.csv, right? So that's the absolute path to our data set. We've worked with other people and done some kind of sharing of programming related things. This absolute path is the thing that becomes really problematic because, for example, on my computer, the data set is located with the name Daniel in it, but typically that's not going to be your case on your computer. It might be Anne, for example, right? And in which case that file doesn't exist on your computer, so now nothing works. And so you try to do everything in relative path if you can, and that's why projects are useful. Okay, so another example is, let's say that our very base starting position is going to be in a folder called analysis, right? So now we're in an analysis folder. And how do we get to this data set that's in the data folder? So the way we would do it on our local computer normally is we go up one folder and then we double click data and then we can access our data set. The way we do the up one folder part on a computer is these two dots. So these two dots from a computer's perspective point of view means up a folder. So if you want to go up two folders, you say .. right? So all of those dots mean go up a folder. So if we're in the analysis folder as our baseline, the way we get to the medical data tumor growth data set, relatively, we say .. data/medical data tumor growth because we're going up a folder, then back down to data. Or we can give the full path. In this current example, the full path doesn't change because we didn't actually move the location of our data set. And so in our current data set, there should be, actually no. So let's say we have this example. We have a file folder structure that is, users, Daniel. I have a projects folder on my computer. I have two projects. One is like a chart review, and the other is some randomized controlled trial study. Each of those have their own data folders. So my chart review has a patient CSV folder, and I also have an analysis folder. My randomized controlled trial project also has a data folder, and there's a patients.csv folder. So one exercise that I'll give about 30 seconds for is, let's say that we are in the chart review folder, in the analysis folder. So we're right here. You're working here, this demographics.r. How would you write the relative path to the RCT data patient CSV file? And how would you write the absolute path to the patients.csv file? So it'll take about a minute. Type it out, or you can think about it in your head of what you would type. This part is important because when we actually start to load a data set, this is literally like what we would type when we start loading those data sets in. So for the solution, the relative path, if we are starting from this demographics file, if we were on our actual computer, we would first go up one folder. So we're out of the analysis file into the chart review file. Oh, okay. So we need to first get out of the analysis file. So we have ... and then we need to get out of the chart review file. So we have another ... and then we can go into the RCT folder, and then data, and then patients.csv. So that is the relative way that we can specify this file. And then the absolute way we specify this file, this is how we would type it if we're on a Mac. We would say /users Daniel projects RCT M220305 data, and then patients.csv. Right, so those are the two ways we can specify this file. If you are working on a Windows machine, notice sometimes when you open up a Explorer window, you can see the actual full path of a file on Windows. The problem with on Windows is it uses this backslash as how it separates different folders. So in R, or in every single computer language and computers in general, that backslash actually is a very special character. So on Windows, you typically have to type 2 of those backslashes, which is a little bit more work. Or on Windows, if you copy the whole thing on how to specify file, you can replace the backslash with the /, and that would work in R. Well, so you don't have to type it twice. So that's one of the weird quirks with Windows, and that's just sort of how you work around the quirks with Windows. So we talked about setting your working directory. This ds4biomed project, you can use this file panel on the bottom right hand side, and one way you can open up the project is you can literally click this ds4biomed, and it will open. So if you have multiple projects on your computer, that's how you can navigate to open it up. Or you can click on the projects tab on the top right corner that I showed you earlier. And what that will do is set your starting point to this location where this ds4biomed file is, right? And so knowing the starting point is first step in trying to load a file onto your computer. Okay, so we're going to load our first data set. The data set that we are going to load is the last example from the spreadsheet example. So I'm going to go through this example with everyone. So in RStudio, we are going to create a new file called rscript. We can save this file and save this as 01 load. And what this will do is create a load file in our RStudio panel. And this was sort of the reason why I was telling you like to put numbers in front of your scripts. And you can do this for your data sets as well. Computers will by default sort your files in alphabetical order. And so if you're working on a project, or if you have multiple Excel sheets and you need to look through them or process them in a certain order, the way you can make those Excel sheets sort properly is putting a number in front of it, right? And this way you don't have to, jump around all over the place when you're trying to go through something in a very specific order. So this applies for your data sets. This applies for code that you write. You can already start seeing, like, because I wrote 00 RStudio, that was like the very first thing we wrote. 01 load, that is the code that we're going to write to load our first data set. And this starts the process of pipelining. So if you have an Excel file and there's one thing that you learned today, and that is really interesting, like whether or not it's loading a data set, doing a transformation, or creating a figure, if that's the only thing that you take away, like drawing the figure from a data set that you load, or taking in an Excel file, doing a bunch of summary statistics, and then saving out the Excel file, this is how you create pipelines. And so you load in a file, you do one thing, and then you save out that thing. And then you can do whatever you need with it afterwards, right? So think about all of this stuff as small incremental changes to your already existing workflow. And the way you incorporate these things slowly is by creating these very small files that like essentially do one thing, and then you pipe it along to your next step, right? So the first thing that we're going to do is, I mentioned tidyverse at the very beginning. And so that is the system of functions, packages, and functions that we will be using to help manipulate data. And so the way we load up the tidyverse is we type library, and then we type tidyverse, and we hit Control Enter to run it. That bit in the chat. And when we type library parenthesis tidyverse, it's going to load up all of these other packages for us in R. One of those packages is a function called readR, which lets us read tabular data sets, so like CSV files. There is another package called readExcel that will literally allow you to read in an Excel file, and you can specify an Excel sheet to read in. So what we're going to do is, after we loaded up tidyverse, there is a function called read_CSV. That lets us read in a CSV file. And so the difference between a CSV file and an Excel file is a CSV file is essentially an Excel file completely stripped of all of its weird formatting. So like the colors that you might be using, the formulas that you might have might only be saved as the values and not the formula. So the CSV file is the plain text version of your data set that you're looking at in Excel. And the reason why that's essentially more preferable than Excel files outside of your current existing workflow is that it is easily machine readable. You don't need to rely on the other person having Excel or that particular version of Excel. And what's also nice is you can preview these files without having like additional programs. And it is essentially like the easiest way for a computer to understand. And you don't need additional tooling to read in Excel CSV files where you do for Excel files. So in this read Excel file, we can load up a data set. So the data set we're going to load up is in this data folder. So we can click data. We can click on, there's a bunch of data sets in here. There's also a folder called spreadsheets. And we're going to load up this exercise 0105 file, right? And so the way we specify that is we're going to put in quotes. So we can use double quotes or single quotes. And then in here, this is why we went through that whole process of specifying files, is because we specify, this is where we specify the location of that file. So we have data/spreadsheets. So we can hit the tab key and RStudio will pick up the fact that we're trying to load up a file. So it's going to give us all of the files as we're typing it. So if we say data/ and we hit the tab key, which is to the left of the letter Q, it'll slowly start opening up this little window that lets us go up and down, and we can select spreadsheets and we can hit tab again. And then we can scroll down to the file that we want, which is called 01 exercise 010050. I will paste this into the chat. And if we run this, you'll see that it will, by running it, we can select everything, hit Control Enter. It will take that CSV file and it will load it into RStudio, and it'll dump out a small snippet of it at the bottom left. And so that's loading up our first data set. If we want to be able to work with this data set, we don't want to have to reload this file every single time. And so what we do is we want to save it to a variable. We don't want to write this read CSV, et cetera, every single time we want to refer to this table that we have in. And so we want to save it to something. And the way we save it is we create a name that we want to refer to this. This can be any name that you want. So maybe we can call this spreadsheet underscore, we'll just call this spreadsheet. Right, so now, if I want to refer to this entire data set that we loaded in, I can just say spreadsheet instead of this whole thing that we just typed. And the way we save it is that there is this operator, this assignment operator, which is the way we type it is the less than and then the minus sign on our computer. So it's two symbols. Then we can copy this read CSV bit. And now if we hit enter, and I will paste this. Now when we hit enter, we don't see on the bottom left-hand side the data set that got printed like before. But on the top right side, what you should see is in the environment panel, this spreadsheet thing should have popped up, right? And it's called spreadsheet here because we literally named it spreadsheet in our script. And now if we click this, like click the word spreadsheet, it will open up the data set that we loaded, right? And so you can see that that data set has first underscore name, last underscore name, time, diastolic. This is pretty much that first example that we worked with, right? So if you're working with CSV files, this is how we can load up a CSV file. There's a few other tools. There's another way you can also load up Excel files, which we will, I think. So there is another way that we can also read Excel files. So if we click on the little tab on the top, oops, create a new line down here. So there is a different library that I believe Tidyverse installs but doesn't load for you, and it's called readxl. So we can say library read the letter X and a letter L. This gives us the functions or the ability to load up Excel files. So readxl, after we run this bit of code, we should be able to run a function called read_Excel. So it's read_Excel with a set of round brackets. And now if we point the file in there to an Excel file, it will load up an Excel file for us. So here in our data set, under data, there is a file called medical data tumor growth.xlsx. So there is an actual Excel file in here. So if we say data slash medical data underscore tumor growth .xlsx, and we save this file to a variable called tumor_xl, and we hit enter. So I will copy that bit. You can see on the right hand side, it took that Excel file and we have that tumor growth data set loaded into R. And in here, there is the feature. So if we click on, if you put your cursor between the L of Excel and the opening parenthesis and you hit F1, on the right hand side, it'll open up the help menu for this function. In this function, if you scroll down a little bit, there is readxl. That's the function that we're using. The first object that it takes is the path. So this is the location of the Excel file. The second part is called sheet. And if you have multiple sheets in your Excel file, you can provide the sheet. So I think Excel, the default is like sheet 1 or something. So if you named your Excel files and it has multiple sheets and you want to load up a very specific sheet, you can say sheet equals and then in quotes the name of your sheet, and it will load that file in. And this ties back into that first chapter that we went through of setting up your data set. When you want to treat your data as actual data and not as a visualization or as anything that isn't data, because now that you're loading in that sheet, if you're running like small one-off calculations, like, oh, I have all of this data, let me select all, let me like click on a cell down here and say equal and then sum and then drag our values and it calculates the sum. That sum now, that single value now becomes part of the data set. And if we load that in, we're going to load up all of our data, but then we also have this random one-off number in there, and that will throw everything else. Like, it will either cause a problem because there's a bunch of white space around everywhere, or, you know, maybe there's a color somewhere, and I think readxl can handle colors by throwing it all out, but this is why you don't want to have those small one-off calculations. So if you are working in Excel and you know that something's going to be loaded or passed on to someone else, do your one-off calculations in another sheet, because you can still do references to another sheet from another sheet. So do that if you're still in the Excel workflow, and that will make everyone's life easier, like down the line. You can always, you know, make a copy of the existing sheet and call that your personal like quick descriptive sheet, but use this other sheet to do the data loading. All of this are ways to make sure that you're not messing with the original raw data, because that's the most important part. Is you don't want to do a lot of data manipulations on the raw data set because there's no system to track what's been changed, right? So if you've ever opened up a data set and went control find and replace, and you replaced a whole bunch of stuff, and then you get a new data set like 6 months down the line, you will have no idea of what find and replace operation you just created 6 months ago. And so the more you can keep the raw data set intact, the better. So we have this Excel data set loaded in, right? So we can do things with this Excel data set. One of the things that we can do is select different columns of our data set. So maybe we only care about a few columns and we don't need to look at all of these other things, for example, right? So this example is a little trivial that 5 columns, we can always keep 5 columns. But if we have 100 columns, we might not need all 100 columns. So one of the things we can do is filter our data set by column. If we have our data set already loaded up, which I'll just paste into that one more time if you have. We have the tidyverse, if we already at the very top ran library tidyverse. Tidyverse comes with a function called select. And what select will do is it will select columns for us. So the way we use select is we pass in the data set that we want. So in our example is this tumor underscore XL. And why I'm using underscores is because computers in general do not like spaces. So if you know that some form of your data set is going to be passed on to like an analyst down the line, you want to limit the amount of spaces that you use. This includes like your column names, although the analyst will probably throw away the spaces in your column names during the analysis part. But you definitely want to make sure that your file names themselves don't have spaces. And the way you can get around instead of typing the actual space is using an underscore. And start working with data sets in this manner, you'll slowly realize that capitalizations and spaces, while it will look nice on your computer when you're browsing, become like you can make so many typos because you forget the capitalization, you forget the space, computers read spaces differently, etc., etc. So you want to use underscores for spaces if you can. And I personally use dashes to separate like important things, like 00 dash, like this is the first script you want to run, dash, and then, load underscore data. Use dashes for like parts between dates, and then underscore like what is this file, right? So you want to eventually get rid of capitalizations and spaces if you can. So in our tumor dataset, there is a column called size with a capital S. And if we only want that particular column, we can type size, S-I-Z-E, with a capital S. And if we hit Control Enter, what R will do is give us a data set that is just the size column. And this is why eventually the general rule of thumb is everyone just doesn't use capital letters because it's hard to remember if something's capitalized or not. So if we were to, for example, use lowercase s instead of uppercase s, we're going to get an error. And part of that error message will say column size does not exist. And it's because lowercase s for size is different from capital case S for size. Say, I don't know what you're talking about. So if we want to be able to select multiple columns, we can use the select function again. We pass in the data set that we want to select from. So in our case, it's going to be tumor, T-U-L. And you can see that as we start typing, RStudio tries to be a little bit useful. So you're going to hit tab and it will like auto-fill things. So this is a really good way to make sure you don't type something wrong, because that's literally the most common mistake. Like usually if I run a piece of code and if it doesn't work, the first thing I'm checking for is to make sure I spelled everything correctly. If we want to be able to select multiple columns, then we literally put in different commas, the columns that we want to select. So in here, there is a group column with a capital G, a day column with a capital D, and a size column with a capital S. And if we select on those, and I will paste this, we can subset our data that way. When you you start looking for tidyverse help online, there is a different way that we can write this bit of code. The way we write this bit of code is we first take the data set that we're interested in working with. So the data set that we're interested in working with is this tumor_excel. There is a pipe operator, so that's percent greater than percent, which is essentially shift 5 period 5. And what this will allow us to do is this will take the tumor Excel and it will feed it into the next thing, the next line of code. Originally, the way we wrote our code is select tumor Excel grouped day size. If we use this piping operation, because it automatically pipes it into the first argument, we can now say tumor Excel. The way we pronounce this is then. So tumor Excel, then select group day size, right? So these two things that I just showed you are actually the same exact thing from our point of view, but you will see people write code like this on the bottom because it allows you to read code from top to bottom, almost like English. So you can say like tumor Excel, then select these columns. Then you can start seeing how this can start piping a bunch of things, which will be more useful later on. So we're at 52 to the hour. Take a 8-minute break until 11 o'clock. What we will do is I will show you filtering rows, how to save out something that you've filtered, and then we'll go through a few descriptive calculations, and then that should be the next block that we would
See everybody at 11 a.m. If you have additional questions or want to ask things, now is also a great time to do that. But also feel free to get up and stretch as well.
Thanks, Ann.
All right, everybody, it is 11 a.m. We are back for our next part of everything where we're going to do a little bit more on statistics and how we can now make different kinds of inferences from the data that we have loaded into R. Dan, take it away.
So where we left off was how can we select individual columns in our data set? The next thing that we usually want to do is start looking at how we can filter our rows in our data set. So the way we do that is instead of the function select, if we want to work on something row-wise, selecting things row-wise, there is a function called filter. The filter function works very similar to how the select function works, in where the first thing that we take is the data set we want to filter, and then the next thing that we pass in is how some kind of check, like an if statement, of how we want our data filtered. So if we look at our tumor Excel data set, there is a column called group, and depending on the group, it's either 1 or 2, and I think there's a 3 in here. 1, 2, 3, and 4. And those are different values for whether or not in this tumor data set, whether the person is in a control group, a diagnostic group, or some combination of the two. And so because we have group as a number, like 1, 2, 3, 4, that's a little bit easier to select. We can say filter our data set such that group with a capital G is equal to the value of 1. And the way we do like equal as a check, and I believe this is the same thing in Excel, you use 2 equal signs instead of 1. A single equal sign is like set the value group to 1. But if we use 2 equal sign, it's saying do a check where group is equal to the value of 1. So if we do that and we run this bit of code, what we get back is only the data sets, or only the rows in our data set where group is equal to 1. And so remember from our first example when I was saying like, oh, how do we filter where our systolic values is greater than 140? You would essentially say like systolic greater 140, and it will filter all of the rows where systolic is greater than 140. We can take this filtering function, which I pasted in chat. We can write it in the piping way, which is tumor Excel, then the pipe, which is pronounced then, filter group with a capital G is equal to 1. And then we can, so these two lines of code are exactly the same. We'll see this bottom one posted on the internet a little bit more. And it's useful because you can say tumor Excel, and without reading the rest of the code, you can say, what's the next thing you do? You do a filter. What's the next thing you do, et cetera, et cetera. It just makes this a little bit easier to deal with. Otherwise, you have to read things from the inside and out, which gets more complicated the more things you start layering up. And we can save these things to a variable. So we can say this is group _1 or group 1 without an underscore, less than dash to do this assignment. And now we have this data set called group 1. And if we look at it, it's only the values where group is 1, right? So think about when you're setting up a data set, leave yourself little trails that you can do these filterings with, right? So maybe you have that flag of like, this is someone I need to report, yes or no. You can say report equal, like in quotes, YES. And that way, when you're looking at your data set from this point of view, you can very quickly just work with that subset of data right away. We want to put in multiple things, so I'm going to it. What if we wanted the values such that group is 1, but also day is 0, like day 0 of our of this trial? We can say day is equal to 0, And what this will do is now you'll see that it only gives us 8 rows back, where the group value is 1 and then the day value is 0. So this is, think of this as like in Excel, I think this is like and. So this is group is equal to 1 and day is equal to 0. We can also use, instead of typing the comma for multiple things, we can say group is equal to 1, and then we can also say ampersand for and this will be the same thing as putting this comma. And so that ampersand is also another way to say and. And the reason why I'm showing you the ampersand for and is because this is how we also, this is a similar way on how we specify or. So if I paste that again, and I will paste. So everything I'm typing, like this session is recorded, so you can follow along after fact. Give us like 48 hours. Everything will be posted on YouTube, and then also the code stuff that I'm typing will also be posted online, and you'll get an email for it. So you can always go back and literally just copy paste from what I'm typing as well. So if you end up getting an error on your end, hopefully it'll get fixed. If you copy paste things, then you'll most likely it's a typo somewhere. So let's say we want to do an or operation. So let's say we want day is equal to 0 or day is equal to 13. And the way we do or is this vertical pipe operator character, which is shift and then the key above the enter sign, which is the same key as the backslash key. Usually you don't really use that key in your normal day-to-day, but you do use it here. So this pipe, this vertical bar is the or operator. And so now we can say day is equal to 0 or day is equal to 13. So you can here, you can start specifying like systolic greater than 140, blood pressure greater than, heart rate greater than 90. And you can start filtering your rows that way. So if you're looking for really specific like bad values or values of interest, you can filter your data set that way. With that, with both select and filter, we can now do both things at the same time. All right, and this is when the pipe operator becomes a little bit more easier to work with, because let's say we want the tumor size greater than 2,000. I think it's but we also want the group, the day, and the size of our data set. So we can say tumor Excel. We want to filter or select our columns first. This order doesn't matter. So we can select our group, day, size, and then we can take that and pipe it into filter. Size with a capital S is greater than 2,000. So this piping is now this is sort of why the piping becomes a little bit nicer to work with, because if you don't care about the code stuff on the right hand side, you can read down this first column and get a rough idea of what's going on. You're taking the tumor data set, you're selecting some columns, and then you're filtering some rows. And then if you're interested, you can read the right hand side to get a sense of what's going on code wise. And so here we have a data set where we only have group, day, and size columns. So we're selecting particular columns. And then we're also filtering the rows such that the size is greater than 1,000. So this might be useful when you only care about the person's last name, their ID number, or maybe just their MRN, and then some information about them, and that's the data set you want to work with, right? So now that we have this filtered data set, let's do another example where we use multiple filtered data set. So we can save anything that we work with into a variable. So let's first write the code first. We can say tumor underscore Excel. We're going to select group, ID, day, size. And then we're going to filter such that day is 0 or day is 13, right? So this little bit going to give us a data set where we have different days and the size. And we can save this into a variable. So we can say filtered gets. So the way we pronounce this, I believe it's pronounced gets. Now we have on the right-hand side this data set called filtered that contains the 4 variables that we specified in select, and then only the rows where day 0 and days 13. So we can click on this and we can see that that is our filtered data set. And now I'm going to show you how we can save this data set out. Typically, saving out an Excel file is a little bit more complicated, and that's also another reason why CSV files are nicer to work with. CSV files are also more interoperable between different systems. So if you want to upload something into something that's not made for Excel, it typically will take a CSV file. I believe a lot of medical record systems will allow you to download files in different formats. Excel is usually one of them, but usually some CSV file or tab separated file is also another option. So we can take this filter data set, and there's another function from the tidyverse called write_CSV. And write CSV will let us take anything that we have, a data set that we have in R, and save it out to a file. And so the first thing that we give it is the data set that we want, so it's filtered. This variable called filtered, which represents our selected columns and filtered rows. And then the next thing that it takes, in quotes, is the location of the file that we want to save it to. So this goes back into relative and absolute paths all over again. And so let's say we want to save it back in our data folder. So we can say data / and then any file that we want. So we can say tumor_filter.csv. So we can go to this files thing and we can make sure that we're in the data folder. And we can see here that now if I run this file, it will on our computer save out this file called tumor_filter.csv, right? So what we did, and this is how you can slowly start incorporating a programming language to do small things and then save out to a file and then just do whatever you need to do to like get your work done. But the benefit of this is sometimes you might actually be given a data set that like Excel cannot open. There's going to be points where like if Excel hits somewhere around like 1 million cells, like it just bogs down your computer. And if all you care about is like some subset of your data set, you can load it into R, subset the parts that you need, and then save it right out. And then you have an Excel file that is actually like you can manage and work with in a reasonable amount of time without waiting like the 15 seconds just so you can click and like see it highlight. So this little connection of reading in a file and saving out a file is literally how pipelines are built. It takes some input, does a thing, and then dumps out an output. And then that output can be given to someone else for their use. You can load it in anything else for your own use, or you can load it into another file that you can use later on. Now we have this tumor_filtered data set, and just like before, we can load this into in another file. And so that's the next part that we're going to talk about. So I'm going to create a new file, and instead of load 01 load, I'm going to name this 02 descriptive. One other thing that's really useful is sometimes this right-hand side gets filled with a bunch of things from a previous project. And if you want to essentially do the actual equivalent of turning it off and turning it back on again without physically closing RStudio and turning it back on, there is a button on the top called Session. We click Session and restart R. What it will do is on the right-hand side, clear everything for you. And this will clear all of the libraries and everything. So this is another good way if something's not working. That's usually also the first thing you want to do, and then rerun your code from top to bottom, just so like you don't accidentally create like these things that you didn't know about. So now that we're in a different file, we have to reload all of the things that we need before. So we can say library tidy. Just like before, where we loaded the medical tumor data set, we can load up that filter data set that we just did. So we can say tumor underscore subset gets the value read underscore CSV, and this exists in the data folder, and then we called it tumor filter.csv. Now, if we look at this data set, this is exactly the data set that we filtered in the previous programming script file that we saved out, and we're in a different programming script file that we loaded back in. Right? And now that we have a smaller version of this, maybe we can start asking, maybe this is like the subset of our data that we care about, right? And what's in here, this is just group 1. Yeah, day 0 and day 13. So maybe all we care about is like, what was the tumor size at the beginning of the study? And then what is the tumor size at like day 13 for all of the different treatment groups? Maybe we don't care about how it's progressing and we just care about the two, like start point and end point. So now we get into the realm of like, how do we start calculating statistics of things? Have this data set. Maybe we want to calculate the average size of all of the tumor sizes from day 0. So how do we do that? Well, we first need to subset our data set such that we have day 0. Say filter day is equal to 0. So now we have all of our data sets values where day is to 0. Now, if we want to work with a single column as not as like a data set column, but as like the actual numbers themselves, there's another function called pull, which like literally like pulls out a single column. So instead of a column of data, we get in R and in the math, and a lot of the lingo comes from math, we get a vector, or really just like, I just want this column as a sequence of its values, not as like a vertical column of data. There's sort of like a small like nuance of things there, but we use the pull function to actually pull out the column and treat it as like, not as a column, but as its actual values. So we can pull out the size column, and you can see this notation comes out a little bit different if we just had used select, because select gave us everything in a column, but if we pulled, it like literally dumped out its actual values. The square brackets on the left actually tell you the position. So like this 41.8 is like position 1. This 46.8 is position 12. This 69.2 is position 34. So it helps you kind of count. So you can say like 34, 35, 36, 37 values are in here. That's what this square bracket stuff on the left is for. It's not actually part of your data set, but it's just to help you like visually count. So now that we have this value, we can literally pipe this into a function called mean to calculate averages. And so this is equivalent to, in Excel, clicking on a cell somewhere, typing equals, and then typing mean, and then selecting a bunch of columns, or selecting the column and hitting enter. The benefit of this for calculating the mean is you're not relying on like, so if your Excel sheet is set up properly in the sense that that one column is only data stored in that one column, you're good. If you're trying to run this mean calculation like underneath at the bottom of like that column, then what you end up having to do is like selecting like A1, cell 1, all the way to, sorry, like A1 to A32, and you're like dragging that little corner. And it's very common that if you start entering new data sets, you forget to drag that corner. Or like if you have a bunch of calculations, you're not dragging those corners for all of those columns that you need. And that is actually the problem of a lot of medical like papers that have to get retracted because they literally forgot to drag the little thing, so the formula didn't calculate properly. This way, when you're running those calculations, it's literally taking every single value in that column, and you don't have to worry about visually checking like all of your formulas to make sure that the cell corner is dragged to the proper location. This allows you, like if you're in a study that you're constantly updating your data set, you don't have to worry about that. The next line that you update and you run this piece of code again, it'll just calculate the new average for you. The downside is you don't see it right away, but that's one of those mindsets that you have to get used to, where your data set is actual data. It's not meant to be treated as a visualization. And so that's where these tools like R and like all of these other things, they're useful because it allows you to replicate those calculations that you would do like much more systematically and without like human error of like making sure formulas are dragged to the right block. So we can build on this more. So we can either, instead of just looking at day is equal to 0, we can say what is the average tumor size for the people in group 2, which is group is equal to 2 and day equals 0. So I believe that is the treatment group. Now you have a way to subset your data off of different slices. So this is something that's a little bit trickier to do in Excel because you have to like set up your grouping, and then you're doing one operation where you're grouping on group and day and then calculating the little formula. And then if you want the overall, that's like a totally separate like thing that you have to do. But in this way, you can have all of these different calculations. One, when it works, it's much easier to audit like what is going on. Like, okay, this is the mean size for day equals 0. This is the mean, this is the mean size for our really particular treatment group instead of the overall everyone else in our study. And instead of mean, you can do things like sum or standard deviation. There's like a whole bunch of other functions that you, I'm not going to cover every single one, but there's a whole bunch of other functions that you can do. One really common one, I guess, if you're dealing with numbers, you can pipe that value, that single column of numbers, into a function called summary, and it will give you the minimum, the maximum, the median, mean, and then the first and third quartile. So if you're trying to get a general sense of like what is going on with a bunch of numbers, this summary function will give you some of the more common statistics all in one go. So the reason why when you're thinking about data sets, I kept talking about like make sure everything only stores one bit of information. And it's because of workflows like this, where you can very quickly and repeatedly make those calculations. But we're here to actually get a sense of what's going on in our overall patient population. And so let's say, for example, we wanted to look at the average size of our tumor at day 0, so the starting point for each group, right? So we're doing this little bit of information here, but we're doing it for group 1, group 2, group 3, group 4. And we want totally separate average calculations. Because it's 4, we could theoretically literally like copy paste this 4 times and change this group from 1, 2, 3, and 4. That's one way you can do it. But there's another way, and in Excel, you can do this as well, where you can create like a grouping variable. And we can also create a grouping variable here as well. So let's say we want the question, so it's really good to like try to, in English, like say the question that you're trying to answer out loud or written down. And you can say like, I want to find the average size of the tumor at day 0 for each group, right? We can, once you say that, so what we're doing, we can use this hash to write a comment. So this is code that isn't going to be written as actual code. So what we're trying to do is average size at day 0 for each group. So that's generally the thing that we are trying to do. So we can use a lot of the things I showed you to answer that question. So what is the first thing? At day 0. So we would filter such that day is equal to 0. And now if we run this, filter of our data set such that day is equal to 0, right? And if you're building these bits of code, it's okay to like do it incrementally. Like don't try to write everything in one go and then hope that it works. It will almost never work. So run these things one bit at a time. So we know that the filtering bit works. Now we want to be able to look at the average size. So remember this little bit of pulling size and taking mean, that's what we want to do. But the trick is we want to do it over and over again for each unique value of group, right? Without having to copy paste this thing 4 or 5 times. You can imagine that like if this ends up being 10 or 20 or 50 groups, that becomes way more tedious to work with. Right, so like that can be like, okay, let's say you're managing like an entire practice that has like 15 different physicians and you're trying to like calculate average like expenditure or like for each doctor. You don't want to do that 15 times because you might forget one of them or some copy paste error. So there is a function in tidyverse called group by, group_by. And in here, you can pass in all the variables that you want to treat as a grouping variable. So in here, we can use group, one value for a group, but you can have multiple things. So if you're trying to look at like the average size of something over time, you might be grouping by the some time variable or the day variable, or group by the group variable and also the day variable. So you can group by multiple columns. But here we're just having one. Then what we're doing is once we know the grouping variable, the code for calculating the mean, I will type it out and then I'll explain it. So average_size is equal to mean of. So let me show you what this code did first and then we can talk through it. What this did was we got a table back. We have one row for each unique value of group. And then for that group, we have the average tumor size. And it gave us that table all in one go. This saves us a lot of time in doing this 4 separate times. And we also now have a nice little table that if we want, we can literally save out to another file. The way this code works is we first specify the grouping variable. So remember in our tumor dataset, there's a column called group that we're using as the grouping variable. And then we're saying summarize. And the reason why we say summarize is because mean is one of those functions that it can take a bunch of numbers and it gives you one value back, right? So the mean of like 135 is one value of 3. That's a little bit different from like if you've ever taken a z-score of something. A z-score will take like 3 numbers and give you 3 numbers back. And so that is not a summary function, that is like a transformation function. So we pipe that into summarize because we know that the value is only one number. We want our data set to come back with something meaningful as a column name. So we can say average_size, and that shows up here. And then the actual calculation, which is mean of the size, original size column. And so this is becomes really useful because now we can calculate a bunch of different other summary statistics, right? So maybe we want to look at the standard deviation. So we can say SD size is SD of size. Maybe we want to look at the min, which is min of size. And so now, and there's like a little comma at the end, so don't. But now if we care about like a bunch of little calculations for each value of group, we can run those calculations. Mean, minimum, maximum are probably the most common, or we can also say sum, but it doesn't make sense in terms of size in here, but it might make sense for other use cases. You can now have different calculations all done for you. And the nice thing is it gives you a nice little table back, right? So you can save this to a variable and then save it out to a CSV file and then give it to someone to look at. Now that you have this sort of table, like summary table of reports that you can do reporting with, if anything changes in that original data set that you loaded in, like maybe that's the data set you're manually curating or you're getting from like Epic or like some other management system. As soon as that data set gets updated, you run this file, assuming you didn't like Control F, find and replace anything. You can now always get an accurate summary of all of this without, doing like, oh, I have to update for this week. I have to download it, click through all of these bits and pieces, and then I get the report. If you spend the time to like do this once, now like if you have to run weekly reports or something, after that initial however long it takes for you to get it working, everything after that is like seconds, which is really just open the script and click run, and you have a data set for an updated set of values. Okay, so next thing we're going to talk about what happens. Oops. So the next thing we're going to talk about is what happens when your data set isn't as clean as I want to select this one column or filter by these rows and then group by. What do we mean by having a dirty data set, and what do we mean by having a data set that's clean? And so this ends up going down the process of what is known as data wrangling or data cleaning. And this all comes from a paper called Tidy Data by Hadley Wickham, published in 2014. And he goes through, tries to talk about data comes in many different shapes, like we talked about in the spreadsheet chapter. And each different shape has a purpose. And that purpose might be to help you enter data easier, but it doesn't necessarily mean it's nicer for the computer to work with. So here's an example of a data set where we have, and this all comes from the Tidy Data paper, so I'm going to walk you through that paper. Here's a data set where we have each row is a person, is a patient, and they have this treatment A and treatment B and some kind of value. This is a made up data set. And you can see here, this is nice in the sense that we can very quickly glance for each person and compare treatment A and treatment B with one another. We can even go and say like calculate the average of treatment A and calculate the average of treatment B and then actually compare those values. He also says that here's another representation of that same data set, and literally the only thing that's different is he swapped the rows and columns. So this is known as a transpose operation. And the data is, the contents of this data set is exactly the same. We can do something like, what is the average treatment value for each individual person if we're thinking column-wise? or we can sum things row-wise or take averages row-wise, et cetera, et cetera. And then he goes to make the case that those two forms of data are fine. And here's a third representation of that data set, which is we have a column called name for each person. We have a column called treatment for AA and B, and then we have a column for the result. And he makes the case that although the other forms of representations of the data is good for you as a human being, this is the format of the data that a computer needs to start doing the analysis. And the reason for that is I just showed you group by calculations. We can now say group by treatment, give me the average result. We couldn't do that in the format before. For example, we couldn't say group by treatment because treatment, there is no column called treatment that contains the values for A and B. It is two totally separate columns. So compare this version, which is a little bit easier for you as a person to read and to see on paper, and compare it to this version, which if you remember from the last exercise that we did, is much better for a computer to deal with and give you results back. And for thinking about making figures, you can start thinking about like, hey, I want a bar graph that is like the average, where each bar represents a treatment of A and B, and then the height of the bar is the average result, right? And we do that by essentially running that calculation of group by treatment, calculate mean result, and then take those values and put it in a figure. And so this notion of tidy data, so this is another one of those terms that that you use to Google when you try to figure about how you should format your data. And there's a very standard definition of this, which says each variable forms a column. So we have a variable for name, a variable for treatment, a variable for the value. Observation forms a row. So each thing that we're measuring, in which case is the value, that is that value for that particular treatment for that particular person. So that observation represents one row. And then each cell only has a single measurement. So that's the thing that I've been mentioning this entire time. Like, make sure there's only one thing represented in that cell and not multiple. And so the nice thing about having those standard definitions is because now we have ways to talk about what does it mean for data to be clean. And then we can have more standard ways, or we can build tools around getting everyone's. We know that data can be messed up in any form, in a bunch of ways, but we can build tools to make them all the same in terms of when they're processed. And so the nice thing about that is when you go through that process, you can then back transform everything so it fits nicer on a screen or it presents nicer, but the computer always has the form that it can do some kind of visualization or some kind of aggregate statistic with. So there's three main problems so data can be messy in different ways, but there's typically three main problems that we will go through. I believe two of them for today for time's sake. And so one of those problems is called column headers are values, not variable names. And this is an example from the actual paper. And so you might have a data set that looks something like this. This is comes from the Pew Research Forum of for each religion and income bracket, how many people were in that fell in that religion and income bracket for that particular study. And this is a format that fits very nicely on paper. So if you're like trying to send this off for like your boss or for someone to quickly look at in a report, this is probably the format that we want to look at. But if we have this format, we can't actually do the calculation of like for each religion and each income bracket, how many people were in there total in our study. That is the actual total. But we can't actually quickly answer the question of like, for each religion, how many people were included. We could make a calculation on the side that's the sum of the row. But we wouldn't be able to say like, what is the average number of people per income bracket? Because we don't have a column called income bracket. And so when you're thinking about processing data, or like if you ever look at a data set and you ask yourself a question and you look at your data set and it's like, I can't do it in this format, it really helps to literally take out a piece of paper and sketch out what are the columns that you want. And so I would actually sketch out, I want a column that's religion, I want a column that's income, and I want a column that's frequency, and this is what I want at the end. Now I can then ask the question, how many people in each religion? I can take group by religion, sum frequency. I can say how many people in each income bracket. I can group by income, sum the frequency. So we can use those same tools from before when we use group by in a data set that looks like this. And so the thing that we need to know about is originally when each column stored its own income bracket, it is known as a wide format. So you can know that like it's very wide. And this is the problem that you get into a lot of trouble with, because if you have very wide columns, remember like Excel will literally run out of columns. A lot of programs will literally run out of columns. So typically you want your data transformed into long. And so this transformation from wide to long is a very common data transformation step. And the way it works is you can see 1x and a becomes the row 1x and a, and then 1x and b becomes the 2x and b becomes the row 2x and b, et cetera, et cetera. So this is the actual data transformation, and it essentially looks something like that. So it is really the same bits of information are literally stored, but it is essentially like the opposite of a pivot table. That's the transformation that it's doing. So we're going to go through that data transformation and how that works. So we're going to create a new script. I'm going to hit session and restart R. So everything that we worked with is we are going to save this file as, so the next thing is going to be 03, and we'll call this tidy. Say library tidy verse and load that function just like before. And the reason why we're doing this again is because we reloaded the session, so everything got deleted, so we're off on a clean slate. So the data set that we are going to load is called tumor. And we're going to use the same function as before called read_CSV. And in here, we're going to specify, we're going to be in the data folder. We're going to load the data set called tumor long, even though it's a wide data set. And that's part of the reason is like, I have to clean the data set to, for a teaching example. And so this ends up being the long form of the teaching. I should probably rename. But this is the data set that we loaded up, and it's exactly the same format of that data set. It's the same tumor data set from that we've been working with, just looks a little different. And one of the signs that you have this problem of columns being stored in variables being stored in columns holding variable names is if you look at your columns and each one of those new columns is actually just a different value of the same variable. So we can see like this is day 0, day 1, day 2, day 3, day 4, et cetera, et cetera. And that is one of those like hints that you have this data problem. When you're collecting data, this is probably the format that you'll enter data because it's easy to say like, okay, I'm working with patient 102 today. And I have all of these days for days of the week from 0 to 28. And today's reading is day 17 in their study, and I put a number there. And so this is when you're filling out your own spreadsheet, this is probably the format that you're going to be, if you're manually entering data, this is probably the manual format that you're working with. But the problem is we can't then ask the computer to run those calculations. And I'm not like that proficient in Excel, but I know like how do I get the average tumor size across each of the days? Like that would be a little tricky for me to actually do in Excel. And so we actually need to transform this data into something that we can use later on. And if all you get out of today is, hey, that one function that Dan is showing you is super useful, and I know how to do that really quickly in R, and if all you do is load an Excel file, do that one thing, save it out to an Excel file, and then do your thing later on, I would call that a win. So we have this data set, and we have a very similar problem to that Pew Research data problem. And what we want is, if we go back to our data set, we want a column that's called group. We want a column that's called GRP, a column called ID, but we want a column that says day, and we want a column that says size, right? So we're trying to remake that data set again. And so the way we do that is, remember, this is a wide data set, and we're trying to make it into a long data set. And so when we use tidyverse, there is literally a function called pivot longer that will do that transformation for us. And the way that works is we take that data set, and it follows the same paradigm as before, as select and filter, is we take our data set that we're interested in, we pass it into the function that we need, in our case, pivot longer. And the way we need to specify, the next thing that we need to specify is all of the columns that we want pivoted down. And so if I look at our data set, the columns are sorted, which is nice. And we want all of the columns from 0 all the way to the last column, which is called 28 in our case. We want all of those columns pivoted down. And so the way we do that, because they're in a special, because they're in sequential order, we can say we want column 0. So this is using the backtick 0, not the quote 0. And the backtick is the key to the left of the number 1. Probably another one of those keys that you never type unless you're programming. So this is from 0 all the way to the column called 28. And if we run that, so we can use 0:28, and this is the R or the tidyverse way of saying I am selecting all of the columns from the column named 0 to the column named 28. We're using these backticks. Part of it is because variable names, column names should not start with a number, but in our case, they do start with a number, so we're trying to deal with that. So we have to give it a little more of a hint and say, like, we're referring to the column 0, not the number 0. And if we run that, we actually see that R would have pivoted all of those columns from 0 to 28, and the value, that cell value here, became another column called value, and it pivoted those columns that way. If we want, since we're in the process of cleaning data, there is another parameter in here called names_2, and we can give it, when it does this pivot, what do you want this column name to be called? All of these columns that you just selected, what column do you want that to be called? And we'll call that the day column. Then when it does that pivot down, what is this other column that gets created? What do you want to call it? By default, it's called a value, but we can say values_2 is equal to size. So now we get a data set where we have a column called day and a column called size. And that's exactly what we want. Now, because of that, we can save this into a variable. So we can say tumor_tidy gets that value, and I will paste. We can now have this, because we have this data set now, we can then go back to what we showed before And we can say group by the group and the day, and I want to get the average size by calculating the mean of size. Part of the problem that we see is we get these bunch of NA values, and that's because if we looked at our original tumor, not every day has a value. So when R gets the value of like, okay, you want me to take the average size for all of the sizes in day 2, this person here doesn't have a value, so I can't calculate it. And so that's why we don't have that number. And that's what R does by default. If it gets a missing value, so this NA that's in red is R's way of saying I got a missing value. If you have a missing value and you try to calculate a mean where one of those values is missing, what comes back is a missing value because it doesn't know what to do with it. So in mean, there's another like switch or a parameter that you can tell it that says na.rm, which says, what do you want to do with the missing values? So rm stands for remove, and true in all capital. And what that will do is like, okay, I want you to calculate the mean, but if you see a missing value, treat it, just ignore it. So it's not treating it as a 0 because that will mess with the denominator, but it'll just skip over that value. And so now we get a data set for each group, and each day we have an average size. And that's something that's a question that we couldn't get before. So if we compare the original question, how would we have calculated the average tumor size for each group and each day when it's in this format? I actually really don't know in this format, like how I would go about doing this. I might like select these groups, select only the values for 0, and then write the mean for that, and then create like another set of tables like based off of like selections, which is great if you're trying to do something super, super quick, but it's not replicable. Like as soon as this data set gets updated, you have to redo that entire process. And that is something that's not feasible. So now after we do that pivot, we can very quickly go back to those aggregation steps from before and actually answer that question. And now you can see, how does the average save this to a tumor? You can see like for group 1, the average size is increasing. And for group 2, the average size is increasing. And where you can start doing those comparisons. One of the problems you see here is that this number is actually not sorted correctly. It's going from 0, 1, 1, 0, 1, 1, et cetera, et cetera. And it's because it's not treating this column as numbers. It's treating the columns as like, how would I sort this if these numbers were in a dictionary? So there is a bit of code to deal with that. I will type it, and you can use this as a reference, but I won't go into that much detail on how it's working. So we can pipe this because we have this data set. There is this function in tidyverse called mutate, and mutate is the function you use if you want to modify a column, either by creating a new column or modifying an existing column. And the column we want to modify is this column called day. So we can say day is equal to, and the problem is, if we look at how R loaded this up, you can see underscore day, underneath day, it says CHR for character. And that means it's not a number, because a number would be like a DBL, or for double, for like a floating point number, which is the computer scientist way of saying this is a number with a decimal. So we want to convert this day character into the number. So how do we do that? There's a function called as.numeric. Pass it in day. Okay, so that's not an error. That's just something that it spit out at us. And now if we look at mean, you'll see that the day column is now a double for number. And this is one of the, and then we can rearrange our columns. So we can say arrange by group and then arrange by day. And so this part now, if we look at this data set, it would have sorted it correctly. And the sorting part is done by this arrange function. And then the mutate function is what, along with this as.numeric, is what converted the character into a number. So you can arrange by, so arrange is like the little sorting. How do you want your rows sorted in your data? So that is what you do when there are variables stored in a column. Another very common, the next common data problem that we have is variables stored in one column. And so because we're at time, we will take a 5-minute break and we'll cover this example. And then after this example, we will go into plotting and visualizations. And so come back at 12:01 and do the last bit of the data processing and visualization bit.
All right, we're here at our final hour for everybody, and we're going to go towards visualizing our data as well. Please feel free to snack as we're going through this. It's no problem. We know it's the lunch hour, and I'm going to turn it over to Dan.
Okay, so a small recap of what we've covered so far today or this morning is we went over thinking about how data shows up in a spreadsheet when we're manually inputting data or when we get a spreadsheet of data. When we have a data set, we're thinking about how we can make that data set more conducive for doing data analytics work. And that could be very simple calculations of, looking at averages or other group statistics. And we follow like those good data practices. It does give us the ability to work with data sets when they're coming in from all sorts of different data feeds. And so hopefully what you've seen so far, I am hoping that there is an example of your actual day-to-day that this can apply to. If not, or if there's something that you get stuck with, you can always contact Dave, that will contact me and Anne, or contact us directly, and we can help you with a lot of your data needs or problems. So just feel free to email us. And then at the end, there will also be a bunch of links and contact information and stuff that you All right, so the last part of the data cleaning part that I want to go over, and this is, this is very common if you're trying to pull data from like the CDC or a lot of like health data stores. Data gets represented in this format pretty often. And this example that you're looking at is for every country and year and gender and age bracket, how many tuberculosis counts there were. And this is a format that is pretty common in the health world. And you can see that the problem, looking at this title, it says multiple variables stored in one column. And if we look at these columns, we have a problem that's similar to the problem we said before. For example, when we had day 1, day 2, day 3, day 4. The problem that we have now is this column, M014, stands for male 0 to 14. The next column is males 15 to 24, et cetera, to female 0 to 14, and then the rest is just cut off just so it fits. And so you can see that there's a similar problem in that our columns represent variables. The other problem this has is that, for example, this 52 represents this particular country at this particular year, but this 52 represents two things at the same time. It's encoding both gender and age group, right? So that's a problem because we now don't have the ability to separate out this 52, what it encodes. There's two things encoded into it, right? And one of those last rules was every number or every cell should only stand for one bit of information. And this is an example where we have a cell that stands for 2 bits of information. And the reason why I am showing you these data transformation steps is mainly so when you do get a data set, or if you're curating your own data set, you create the data set that's easy for you to create, and then you can handle the messiness if you know that there's a process that exists. So I know there's a lot being thrown in this workshop right now, but a lot of it is just seeing like what is like just possible that you can do. And if you know what's possible, then it should make your life in terms of data curation and looking at different forms of data a little bit easier because you now know what is possible. So you would be able to know or figure out or look up what the next step would be. And so given this data set, we actually need to go through 2 steps. We first go through the step on the left, which is very similar to the process we had before, which was taking all of those columns from M014 to F, whatever age group is at the end of our data set, and pivoting it into long format. And so we get this long format data. That's most of the way there, right? We still have this problem where, for example, this 10 at the very bottom encodes for males age 65 and above. Then the next thing we do is we go, if I were to tell you, like, without any programming like knowledge, if I were to just give you like, hey, we have this column and this column literally says M014, how do I split out the M part from the number part? And if before even thinking about like how would you do this in a programming language, you might, like, if I were to have you do this like on paper, you might say something like, well, you take the first character and you make that the sex column, and then you take the other numbers and you make it the age column, right? And that is something that we can do in a programming language. In Excel, you might have to some of the substring functions or something like that. So you would be able to do that in Excel as well. And so this is the process that we're going to mimic. So we are going to replicate that exact problem, I believe. Yes, we're going to replicate that exact problem in the paper in R. So we're going to load up a new data set called TB for tuberculosis. We're going to use a read_CSV function. So this is the same function we've been using to load up a data set. We're going to say our data set is in data/TB. And you'll see that if we look at this data set, we get exactly the same data set from that paper that we're looking at, right? So we're going to go through the same steps that we talked about earlier. So the first step that we're going to do is take all of the values from M014 from this column all the way to the last column called female unknown. And we're going to do that pivot longer transformation. So we say TB, then we use the pivot longer function. And here we specify the columns that we want. So we can say we want the column that begins with male 014. So we can say start with male 014, colon, all the way to female unknown. So female. And we get that transformation. Not every single bit, not all of our columns in our data sets are going to be sorted where we can just say start here, end there, right? So in Tidyverse, there's a bunch of other helper ways that we can select different columns. So there's a whole bunch of ways you can select different columns. But another way that you can do is look for a pattern, right? So how do we know if we wanted all of these columns, M014, M1524, et cetera, F5564, what is one way we can specify all of those columns? Well, one way we can specify them is if the column begins with the letter M or begins with the letter F, those are also columns that we want to select. So if it's not feasible to select from one point to another, you can select based on a pattern. And one of the patterns is we can start with a pattern, we can contain a pattern, we can end with a pattern. The start with, end with, those are really useful for survey data because the survey data usually comes in as like Q1.1, Q1.2. So you can select your data based off of like starts with Q1, et cetera, et cetera. So another way we can do that is there's a special like selector helper. So we can say starts with C, M, and F. What this will do is this C is R's way of saying, hey, I need to pass you like a list of things, like multiple things. So this is R's way of saying like, hey, I want you to select all the columns such that the columns start with multiple things, those multiple things being starting with F, starting with M and starting with F. And so these two bits of code effectively do the same thing because of the way our data is structured. If our data was all sorted, where like males came first and then we have like the demographic stuff and then females came after, we wouldn't be able to do this type of selection because they'll select those columns in the middle that we don't want, and we would use this type of selection. So that's the small differences there. And so there's a lot of different ways you can select columns, not just one range to another or starting with, there's a bunch of other ways you can do it. So we're going to save this to a variable called tb long, because we now have the long of our data. And this is, just like the paper example, most of the way there. So the next part is, how do we break up this column into two columns, one called sex, one called age group, and the way we would break it up is literally chopping off the first character. Certain examples, it could be the first character. Maybe when you're creating your own data set, you might have m_014, in which case you can use the underscore as a marker to split your column. So that's when you're putting together your data set, always think about how you can leave breadcrumbs for you to deal with later on. What you don't want to do, for example, is do something like call your column male 014 and then female 014. That becomes a little bit trickier because you don't have a special character that you can use to be like, oh, split by the period or split by the underscore. And it's harder for you to be like, oh, just cut off the first 4 characters because male and female have different character lengths, right? So when you're putting together data sets, and the reason why I'm showing you all of this is because you know of the tools later on in the data analysis pipeline or data processing pipeline, when you're curating data, you can leave breadcrumbs so you know how to deal with it later on. And that's super important because that will make or break the ability to do something or not in the like time span you have. And so in our case, because we use a single letter designation, we can say split by the first character. And that splitting and all of that stuff, that comes from a function in the tidyverse called separate. The way separate works, it takes a data set, so that's why there's another pipe. It takes this entire data set, and then you give it the column you want to work with. In our case, the column we want to work with is called name. So we're going to do some kind of separation function on this name column. When we do the separation, we want to split it into how many columns that we want. In our case, we're expecting 2 columns. So this is another place where we're seeing this C again because we're expecting multiple things. We're expecting a column called sex, and we're expecting a column called age group. The way we are separating is by chopping off the first character. So we can say sep equals 1, which is if we give it a number, that's how many characters to cut off. We can put in like quotes like an underscore if we're trying to separate on an underscore. But in our case, we're separating on the first character. And so now if we're looking at tb long, what it did was it took the name column from before, converted it into those 2 columns, sex and age group, and split on the first character. And so now we have a proper data set. And if we go back to all of the data transformation stuff, now we can say for each age and for each sex and age group, how many people were there, right? So we can now go and do those calculations like, oh, we can group underscore by age group, and summarize sum of value, right? And this value where na.rm is equal to true, so we can get numbers. And you can see in total from all of the years in our data, there are like 27,000 people with TB cumulative in that. Or we can break this up by year. And now we can see in the year 2000, for all of the people age 0 to 14, there are 27,000 people, right? So now because our data is in a cleaner format, we can start asking these questions. And these are the questions that help us answer some, like the thing that we care about, right? And it doesn't matter how Epic gave you that data set, as long as there's like those little like breadcrumbs on how you can like pivot and manipulate your data sets, you can start asking those questions. And these are like the insights that matter because some decision will be made from looking at like these aggregate statistics. Okay, so the last thing, there's one more format, data format, like we showed you the pivot longer. There's technically another way where you can go the opposite way, called pivot wider, and that's less common in dataset examples. So we'll skip it for now just so we can go to the data visualization portion. Because we've done all of these calculations, it would be nice to actually like look at it in a figure, because that's, people respond to figures way better than a wall of numbers. So this slide deck is pretty small because we'll go right into actually doing this stuff in R. The most important thing when we're talking about visualization is knowing the types of data our column is storing. So data can come in different formats and all of stuff, but like the value that that data represents can be nominal. So like those are unordered descriptions. So like sex is a nominal variable. There's no order between male and female. It's just male is one example, female is another, and then you have a bunch of other gender neutral sex options. You can have study parameters. So whether you're in a treatment group or a control group or some combination or whatever, there's no real order to those. So those are nominal variables. And then you have variables that are ordinal. So Likert scales are usually ordinal when you're essentially saying on a scale from 1 to 5, how do you feel today, from 1 being bad and 5 being good? There's an actual order to those values, right? Like 1 is less than 2 is less than 3. You can have completely numeric numbers, right? So like the size of a tumor is continuous. So it can be like 1, 1.1, 1.2, 2, etc. So you can have numbers that are completely continuous. Continuous numbers are still ordinal because there's an order to them. One is bigger than the other. And another type of variable that's really a subclass of ordinal or nominal is a binary variable, which is simply a yes or no question. And in the health world, usually that question is, did this person get cancer, yes or no? Or did this person die, yes or no? So that is a binary variable. And it's important to know about that because depending on what type of variable you're working with, that completely dictates what type of figure you can work with. Right, so there are many times where like I try to draw a figure and I get a figure up, but it makes no sense because I've picked the wrong plot for the data I'm trying to plot. Right, so knowing this is the first step of creating a good visualization. The next thing is I'm going to be showing you this visualization library called ggplot2, and this comes from essentially there was like a 4-hour workshop that Thomas Lynn Pedersen from our studio, he's the current maintainer of ggplot2, did on YouTube. And I think I can link that. I think it's linked somewhere in the slide deck. This is one of the slides that he had. And essentially the way ggplot2 works is it's a layering system. You first specify the data that you want to work with. Then you specify a mapping. And that mapping essentially says, I want the x variable, the x-axis to be this variable, the y-axis to be that variable. I want the color to be that variable. So any mapping from column value to the figure is in the mapping layer. Then you have a few things in the middle like statistics and scales, which most of the time they're calculated for you automatically. And then the most important one is the geometry, which is essentially saying, okay, so you gave me the data, you told me X is going to be size and Y is going to be, X is going to be day and Y is going to be size. You haven't told me what type of plot you want. And that what type of plot you want is the geometry layer. So you can have like a line geometry or a point geometry for scatter plots, or a bar geometry for bar plots, or bar graph, or box plot for box plots, etc., etc. On top of that, there is a faceting layer, and this is probably the coolest part about ggplot2. This is the faceting layer is literally the reason why I kept. It's the draw into R and plotting that drew me in, because what a facet does is just like how you can do a group by. Remember that example of like group by, group the treatment group, and then calculate the average tumor size. The facet is a group by for figures. So not only can you calculate like figure for all of your data, you can create a grouped figure for each unique value of some other column. And that's what facets give you. And it gives you a very quick way to look at all of your data in different cuts. Then there's a thing like coordinates, which we don't have to worry about. And the theme is the color and background and stuff like that. So that is the layering component in ggplot2. So we're going to go through all of this. So one last thing before we go on to the another file. Everything that I've done here, all of these new processed, cleaned up data sets, whether it's the cleaned up version or the summary statistic version, just like from before, you can save it to a variable, and then you can save it out to a separate CSV file, and you can give that to someone else, right? So that's the other really important thing, is you can do all of this stuff in R, and if you're working with someone else who just needs like the flat file, the flat CSV file, or the Excel file, you can give them that. But then from your end, if your data set from your source changes, you can at least be guaranteed that that pipeline of stuff that you did, there won't really, it's replicable. So like if data updates, so do your calculations and transformations, and you can hand them off to someone else. So we're going to create a new file. We're going to go to session, and then we're going to say restart R. I'm going to save this, and I'm going to name it 04, call it viz. And again, the naming convention is really just helpful. So like when I give you the link to my code, all of the code is like in a proper order, so you can see the order that we're going in. But again, remember, you can use numberings for all of your file naming if you need them to like literally sort in the proper order. Okay, so this is the part where we need that medical data. So if you're on the RStudio Cloud because you couldn't get remotes installed, this is where that part sort of comes into play. So we're going to load up tidyverse, just like before. The plotting library that we're going to be working with is called ggplot2. And the data sets that we'll be using come from this package called medical data. This is a library maintained by Peter Higgins at University of Michigan, and sort of curated a bunch of medical data sets that we can use for teaching purposes. So the data set that we're going to be looking at is a data set of blood storage, which essentially is a cohort of 316 men who have undergone radioprostatectomy and received transfusion within 30 days of a surgical procedure, and its follow-up data. And essentially we are looking to see if there is a biochemical marker for a cancer. And so this entire time, we've been using the read_CSV function to load up a data set. But because this is a data set existing in a package that we installed, we can say blood gets blood storage. So there is a blood storage data set that's available to us when we load up the medical data library. And so now we have this clinical data set from a study. So when we're given a data set, one of the things, so this is a data set with, you can see 20 variables and 316 rows. When we're looking at our data set, there's a few things. This is where code books come in handy because we want to figure out what is going on, what are these values containing. So I can tell you that one of the variables in this column that we are interested in is there is a column called recurrence. And this is a binary variable, 0 and 1, on whether or not there was a cancer marker recurrence after treatment. And so 1 being yes, there was, and 0 being no, there wasn't. And so you can see like this data set is one of those data sets where everything is encoded as a number, which is good for doing the math part of the analysis, but it's kind of annoying to deal with when you're the human trying to figure out what is going on, because you're constantly having to flip back, like what is 0, what is 1, because it could be different. 1 doesn't always mean yes, and 0 doesn't always mean no. So that's one of the things that you have to. Okay, so the variable that we're interested in is the recurrence data, recurrence column. So let's say, for example, I need to figure out what is going on in that column. So I want the number of rows. So how many values do I have for each value of recurrence? So when you start saying out loud sort of like the question that you're trying to ask, whenever you get to the part of your statement that's like for each value of, that's when you use group by. So I'm saying I'm going to group by all of the values of recurrence. So this group by function is something we've seen before. We're going to do a summary. And then instead of asking the sum of the recurrence, which we feel, which wouldn't make sense because we would be summing a bunch of zeros, we're actually trying to get the count. And one way we can get the count is asking for n, like just give me the number of rows. So there's this function called n that essentially will count for us. And so here we can get a summary statistic of, in our data set, for the recurrence of 0, there's 262 rows in our data set, or 262 observations. And then for people with a recurrence, there's 54. And so this ends up being, if you're trying to do a study or trying to do an analysis, this is something that ends up being really important because you're thinking on later on, you're trying to fit a statistical model or something. This becomes problematic because if I were to fit a model and my model is trying to guess 0 or 1, like yes or no, if my model was just saying nobody, there was no recurrence everywhere, I would be right 262 times out of the whole entire population. And then that's pretty good. So that would be like a pretty good model, even though the model is actually useless. And so doing these summary statistics is really important if you end up doing something like a statistical model, but it's also important just to figure out like what is going on in your data set. So let's take this number and let's try to visualize this. Like I said, during the ggplot layering system, we first specify the data layer. So we're going to say, we're going to be using ggplot now. So we say ggplot. The first thing we specify is data. So the data layer is blood. And that blood is the data set that we're working with. So if we run this, you'll see that we get a blank canvas, right? We just said like, hey, here's some data in your base layer. We haven't told it to plot anything. The next thing that we specify, remember, is the mapping. So if we put a comma and hit tab, you'll see that the next parameter that we can specify is the mapping layer. Mapping, the way we specify mapping is a function called AES. That's sort of just one of the weird quirks with ggplot. But we can say here in AES, we want the X column to be recurrence, the recurrence variable. So now if we run that, we get a little bit more stuff in our data set, but remember from our ggplot stuff, we eventually need to specify that geometry layer, like telling it like what is the actual type of figure we want to plot. So the way we add on these layers is we literally use the plus sign, and then we can add on a geometry layer. The way we add on a geometry layer is there are a sequence of functions called geom underscore, and if you type this and if you have ggplot2 loaded, it will give you all of the different types of plots that you can create using geom underscore. And you can also use, if you have census data with latitudes, longitudes, and zip code data, you can also make maps out of ggplot2 as well. So the first plot that we're going to do is going to make a bar plot. And so what this will do is take the recurrence values, so 0 and 1, and then create a bar plot of the count. If we, for example, took this data set up here and calculated recurrence and count, and we saved it to a variable, so we can save this to, let's call this rfreq for recurrence frequency. So for recurrence frequency, let's say we wanted to plot this data set, right? We already did the summary statistic, we already did the aggregate count, but we still wanted the bar plot. In our previous example, we didn't actually have to tell it like, hey, like do the summing for us. ggplot understands that if you give it a column, and that column is sort of ordinal or discrete, it will do the summing for us. That statistics layer is automatically done, calculated and figured out for us. But we can, if, for example, we're doing a data exploration, and we're like, hey, that's something interesting, I want to plot it, we can use ggplot to manually specify those layers. So we can say ggplot data is equal to, instead of the entire blood data set, it's just this frequency one that we just created. The AES is now going to be, hey, we want the x-axis to be this recurrence variable, so we can say x is equal to recurrence. And what do we want represented in y? The y variable is going to be this count column. And I'm going to say plus, and just put a new line just so like it doesn't overflow too much. Geom underscore bar. So we're doing the same code as before, except now in geom bar, we can specify the statistics layer. There's a statistic called identity, which just says, hey, I know by default you will sum everything together, but I already summed everything up for you. So just take the identity, which is essentially saying whatever number you got, that's the number you plot. So we can do that. So let's go on and look at other things in our data set and see what we can do. So within ggplot, we can pass in our blood variable. We can pass in an aesthetic mapping. And let's say we want to look at the distribution of age. So we can set x is equal to age. This again won't plot us anything because we haven't specified the plotting geometry layer. So we can say geom underscore histogram to plot us a histogram of age. And so this tells us in our data set the age distribution. So most people in here are going to be, because it's related to prostate cancer, it's going to be males around age 65. You can see when it will create at most 30 bins for us, and it'll take a guess. But if we want our histogram to be a little like more aggregate, like aggregate more bars together, we can say bins equals to 10. So you see here it says using bins equals to 30, but you can specify it with another number. So we can say, instead of using the default histogram, we can say bins equals to 10, and it'll give us 10 bins instead of the default max up to 30. Right, so that's a figure that's useful if you're working with a continuous variable, so a bunch of numbers, and it's only one thing that you want to plot. What happens if you need to plot two variables at the same time? So there's another variable called T volume for tumor volume, and it has three values: 0, 1, 2, and 3 for low, medium, and extensive for the volume of our tumor. So let's say our question is, how does the tumor volume relate to age? So we have some categorical variable on one of our variables we want to plot is categorical, and the other variable we want to plot is like a number. So we can say ggplot, we're going to pass in this blood variable. We can say AES, and we're going to say X is going to be the tumor volume, so T-vol, and spelling matters, so like I just know that it's called capital T, capital V, and then Y is going to be age with a capital A. When we end up in a situation where you have a categorical variable and a continuous variable, one of the figures that that people are used to looking at is a box plot. So we can say geom underscore box plot. We run this, almost got it right. And the problem here is tumor volume contains values of 1, 2, and 3. And it's counting those numbers, 1, 2, and 3, as numbers. Just like before, when we pivoted the day column and it treated it as character, we had to treat it as a number. We actually now have to go the other way and say, treat the number as like a categorical group instead of the number that it actually is. And so before, when we said as dot numeric to convert like something into a number, we now have to wrap the total volume in something called as dot factor. And a factor in R general is the jargon that's used to say turn this thing into a categorical variable. So a factor is a categorical variable. The tumor volume is going to be a ordinal categorical value variable because 1, 2, and 3 have a specific order to them. And so now if we turn the tumor volume into an actual categorical value, we can now see we get a separate bar for the volume of 1, 2, and 3, and then here we get the age distribution in a box plot. So what's nice about this is now that we specified here on our left-hand side, like how we want to specify which data points go into our figure, we can now swap out like the actual geometry bit. So another very common way to look at distribution is a violin plot. So this is the box plot, except it actually gives you the actual frequencies drawn out in like those little histogram bumps. And if your data does have some kind of skewness, like it's not always like centered around like a nice big bell curve, violin plots are a really nice way of like actually visualizing your distribution. So they encode the same information as this box plot, but if there are actual like skews to your data, I personally feel like the violin plot will actually show you the distribution a little bit easier unless you're constantly used to looking at box plots. So we talked about two variables. Now let's talk about what happens if our two variables that we're interested in are both numeric or are both numbers. So we can say ggplot, we're still working with the blood data set. We're going to say the aesthetic mapping is, let's say we're looking at the tumor volume, which is going to be in a variable called P volume or prostate volume. Let's say Y is going to be it's going to be the variable that represents the antigen level for going to be a reading for a specific thing that we're looking for. And that's also going to be a continuous variable. So that's going to be called pre-op PSA. So just like before, because we haven't specified a geometry, it's going to draw us a blank slate. But if we want a scatter plot, we can say geom_point, and it will draw us a scatter plot. And this is a plot that's useful for when we have two continuous variables. And so I bring this up because let's say we want to throw in more variables into our plot. Let's say we have two continuous variables, but we want to split it off of some other categorical variable. Like let's say we want this scatter plot, but we want the points to be a different color. So in the aesthetic mapping, there is a parameter called color. And we can give color some categorical variable. And what this will do, like when this saves over, what this will do is it'll color each point as a categorical variable. And the same problem we had before, this categorical variable in our data, because it's all encoded as numbers, it's treating it as a number. So we have to say as.factor again. Now we can see like this categorical variable has values 1, 2, 3, and 4, and it'll color those points in our scatter plot according to those to that value. And so we can keep going and adding more bits of information to our data set. And so the last thing I want to talk about is this notion of a facet, which is sort of the reason why I stuck with creating these figures in R, because let's say we want a separate version of this plot for another group. Like, so think about like that group by operation, but I want a plot like this for each one of those groups. And so that's where we can add another facet layer. So there is two ways. There's a facet grid. So grids are like two-dimensional, so you can specify two variables. But the one I'm going to show you right now is going to be called facet wrap. So it's going to be a single column. Syntax is a little bit wonky. We have to use tilde to specify the column. So that is shift and the key to the left of the number 1. So it's the little squiggly line. Here we can specify the other categorical variable that we're interested in. So age dot group. So let's say there's another variable for the age group of people in our data set. And so now if I just hit zoom, we get that original scatter plot from before, where we're looking at the tumor volume by the pre-op PSA, and it's colored by this other categorical variable. But then we get a totally separate scatter plot for each age group, right? So that's that grouping factor that we had before. So we can keep going with this example. Instead of facet wrap, we can say facet grid to specify two variables. And so we can now compare recurrence with that other variable. And you can see that we can now have these figures to try to figure out what is going on with our data set. And this is doing the exploration, getting a sense of what's going on without really doing any actual statistics. And you're trying to get a sense and all of the heuristics for what is going on. And so with all of these plots, you could, the easiest way, I guess for now, for time, there is a way to export these figures. So there, you have a mechanism to do all your data processing, create a plot, and then dump out a plot at the end. And now anytime your original data set gets updated, you have like the system to do the processing and the update your figure without having to manually like mangle your original data set over and over again. So that's pretty much everything that I want to have the last bit for conclusion. And so, yeah, there was a lot of things that we covered today. Mainly, the main takeaways are think about what you're doing when you're inputting data, what its format is, and all of the R stuff today. I mean, there's only so much you can actually retain in a 4-hour block when everything is new, but hopefully seeing what can be done helps you think about your data as you're moving forward. So it's one of those things where, like, the more you see something, eventually somehow you'll understand it, and sort of just keep trying at it. And there is a whole community behind all of this to help you learn this stuff. So in terms of additional resources, and there is a link. So that bit.ly link for the Google Drive has the links to the slides, so you can see the links that I have here. If you want to know more about everything that I'm trying to show you in a more general sense, like all of the stuff on how you can select data, more stuff about plotting, other forms of data transformation, and sort of an introduction to model fitting that we didn't cover today in the first 4 hours, there is a free online book called R for Data Science, written by Hadley Wickham and Garrett Grulman, who are both at our studio. And that is a publicly available book that you can flip through, use it as a reference guide, or use it as a guide to teach more. There is an R for Data Science community, and so there is literally a Slack group that if you go to that link, you can join the Slack group, and pretty much if you need our help, that is one place where you can ask for help. John, I forgot his last name. John, who helps run that community, literally has a system of like TAs that have office hours. And so you can literally like go to one of these office hours and ask for help outside of the context of like emailing David, me, or Ann. If you want to learn more on your own, every Tuesday on Twitter, there is a example data set that gets thrown out called Tidy Tuesday. And it's like stuff about like, movie ratings or words that are used in reviews, or like, I forgot what this week's was, but there is sort of like a random data set thrown out there. And essentially the thing is like, hey, you just work on this one problem, get as far as you can for like an hour, and post your results online somewhere. And if it's as simple as like, hey, I just plotted this for the first time, there's literally a whole Twitter community like that share this stuff. And the reason I bring that up is if you can't actually, for HIPAA reasons, like do this stuff on your current actual day-to-day data sets, this is an opportunity to, one, see what other people are doing, two, to just know what is remotely possible, and it gives you something to work on to continue learning. David Robinson, which I realized I just spelled his name wrong, he actually streams his 1 hour Tidy Tuesday workflow like on YouTube like every week. So you can just watch someone else do a very small data analysis pipeline just to see like what you can do. For Maria and Stephanie, there is a global community called Our Ladies that if you want to learn or ask for help in the context of like just with other women in the field, you can join that group, and they will help you learn this on your own. You can ask questions without any other fear of like looking like you don't know anything, because it's a super helpful community there, and there's a link to all of that. So it is a global community, and it would be nice if there was like an NRV-ish like local group, but that takes a lot of work. So if you want, you can start a local chapter to help build the group, but you do have access to that entire community as well. On top of that, there is a very specific R in medicine community called R Medicine. They do host a conference. It's a really small conference. It's like 200 people, I think, max, tops for the last year. And that And I think like 2 years ago, it was like 50. So it is a growing community of all of the doctors, nurses, nurse practitioners, analysts, receptionists, like anyone who work with medical data or data in a medical context. There is a community that's growing for those people. I'm trying to see if they can just have like a public join list like the R for Data Science community does. But if you email me, I can sort of create like one of those one-time invite links and send you that, so you can get on that Slack group. And you can always contact me and Anne. We're part of the Virginia Tech Data Services, and this is a service in the university library, where we essentially have like consultants, like student consultants, to help you work on a project. So knowing the stuff that I taught you today is a pretty good first step in terms of like, at least you know how to talk about your data set, or at least you might be able to point out like, hey, I know that my data set's messed up and it's because of this, right? And so it's you also being part of the whole pipeline instead of just being like, I have a question, here's some data, help, right? So it's sort of this two-way communication that sort of slowly starts to build. There's my contact information. There's Anne's contact information if you need to email us or just message us in some way, shape, or form. And another thing that's also here at Virginia Tech is there's the Center of Biostatistics and Health Data Science that's located in Roanoke. And that is run by Alexandra Hanlon, who is also on my PhD committee. So, you know, we can always make something happen because it helps Dan graduate. And that's a pretty good motivating factor for people to, to help along. So if you have a research question, so these are the people that are like, the people that work there are the like statisticians. And so all of the super heavy statistics research can questions on like how you set up a research study, and doing the analysis, that is what they're really good for. The data services stuff is less of the stats focused realm, but if you need help with just working with your data and processing it, that's sort of how Anne's group at DataBridge ties in with Alex's group at CBH. So they're overlapping, but they don't overlap. So those are the two other services. What's nice about Alex's group is on Monday and Wednesday, at those times listed, they literally have Zoom walk-in hours. So if you actually have a research question that you want to help talk through, you literally just pop in on their Zoom hours and you can ask the statistician a question and they can help you work out your question. So it's literally drop-in hours. Like I literally call in when I have to do some analysis thing for my dissertation and I have a question. This is essentially the cheapest way you can get an on-call like statistician to help you with something. And a lot of the stuff, the way I'm teaching and the materials that we have listed, ds4biomed is like the book version of everything I'm teaching. So hopefully by the end of my dissertation, this will become like one of the ds4biomed books, but cater towards like all of the data sets are medically related. All of that stuff is inspired by this organization called the Carpentries. So they are a nonprofit organization that tries to teach all of the scientists and researchers and anyone working with data who've never actually formally learned this in school. And so that is a volunteer organization that you can learn more about that whole scientific computing stack, and you can have them help you run workshops as well. And then Nathaniel Porter is the Virginia Tech contact for the Carpentries there if you need. So he helps runs Carpentries workshops throughout the year, so you can contact him and he can help sign you up into the next Virginia Tech Carpentries workshop as well. For surveys, help give feedback. It makes the materials better. This is actually an interesting cohort of people because no one here is like an active student. And so it would be nice to know how this stuff that I'm putting together like fares for people that aren't like the clinicians doing research, or like knowing your background helps like the examples and the way we're creating these materials. So feedback is always good. And you can choose to like have your feedback in the actual be counted part of the research study, or you can just give feedback and skip all the questions and just be like, Dan, you need to like slow down or something. So any of that stuff helps. So with that, I will give it to Anne if she has anything to say for conclusion, and then
Yeah, I was going to say we'll email all of this out to you as well as the link to the video once we get it all polished up. We appreciate your time and for talking data with us today. We'll stick around for any questions. We know that was a marathon of data training, but we appreciate you engaging in with everything, and we hope it's helpful for you in some way in thinking about how to apply it to your workforce in the health departments. So thank you, and thank you to Dan and David for setting all of this up. And that is what we have for today.
All right. Well, thank you, Ann, and yeah, thank you so much, Dan, for walking us through that crash course. And I knew a little bit, but it was really great to just really kind of get the nuts and bolts of how to look at our data and stuff like that. And Maria, thank you for sticking around with us. And I think this recording will be really valuable for folks because we did go over a lot, and it'd be good to go back. And yeah, I'll put all the information, that the slides, and we have a Google Drive as well that we can also share and have those additional resources available. But yeah, really appreciate your time. It was great. So thank you so much.
Yep. Thank you all. We'll see you around. Don't hesitate to contact us as well. We're open to any kind of help and discussion.
All right. Well, thank you. Appreciate it.
Yeah. Bye-bye.
Right, bye.
Bye.
1 o'clock exactly.
Yes, 1 o'clock exactly. I didn't go over. It was great.
You did not go over. It was great. I think everything went well. I really appreciated the engagement we got with Maria and everything like that. So
I appreciate nods.
Yep. I think all of that went